नमः सरस्वत्यै नमः श्रीगुरुभ्यो नमः हरिः ओम् जातवेदसे सुनवामसो ममराति यतो निदहाति वेदः स नः पर्षदति दुर्गाणि विश्वानावेव सिन्धुं दुरितात्यग्निः तामग्निवर्णां तपसा ज्वलन्तीं वैरोचनीं कर्मफलेषु जुष्टाम् दुर्गां देवीं शरणमहं प्रपद्ये सुतरसि तरसे नमः अग्ने त्वं पारयानव्यो अस्मान् स्वस्तिभिरति दुर्गाणि विश्वा पूश्च पृथ्वी बहुलान उर्वे भवातोकायतनयाय संयोः विश्वारिणो दुर्गा जातवेदः सिन्धुं ननावा दुरितादिपर्षे अग्ने अत्रिवन्मनसा गृणानो अस्माकं बोध्यविता तनूनाम् पृतनादितगुं सहमानमुग्रमग्निगुं भुवेम परमात् सदस्तात् स नः पर्षदति दुर्गाणि विश्वाक्षामद्देवो अधिदुरितात्यग्निः प्रत्नोषिकमीड्यो अध्वरेषु सदाच होतानव्यश्च सत्सि स्वाञ्चाग्ने तनुवं पिप्रयस्वास्मभ्यं च सौभगमायजस्व गोभिर्जुष्टमयुजो निषिक्तं तवेन्द्र विष्णोरनुसञ्चरेम नाकस्य पृष्ठमभि संवसानो वैष्णवीं लोकइहमादयन्ताम् कात्यायनाय विद्महे कन्याकुमारि धीमहि तन्नो दुर्गः प्रचोदयात् ॐ शान्ति शान्ति शान्तिः
Om Shri Sai Ram. Seeking Bhagwan's divine blessings, I welcome one and all to the second day of the two-day international webinar on Physics for Healthcare organized by the Department of Physics, Sri Sathya Sai Institute of Higher Learning. Today, I am here to introduce the first speaker of the day, Dr. Shuvan Prashant Turaga, a Senior Research and Development Engineer, Atonic Systems Private Limited, Singapore. Atonic Systems is a startup dedicated to realize fast, portable, and compact spectrometers for multifold applications. Sir is actively involved in product strategy and development teams of the Atonic Systems. He is also a key member of algorithm development and signal processing teams. Dr. Shuvan is one of the prestigious alumni of Sri Sathya Sai Institute of Higher Learning. He completed both his BSc and MSc degrees from our very own institute. Then after, he obtained his Doctor of Philosophy from the National University of Singapore. He was working on the area of terahertz optics and metamaterials. He developed two-photon lithography system and terahertz time domain spectrometer, and also designed metamaterials for designer dispersion using coupled structure. From July 2015 to January 2017, Dr. Shuvan was a co-founder and tech lead in Kiranam Labs Private Limited. This startup's aim was to commercialize visible light communication, also known as Li-Fi. However, The startup was prematurely closed due to a business decision. Then after, Sir joined as a research fellow at the National University of Singapore, where he worked on the area of diamond photonics. In 2018, Sir joined the Atonic Systems as the Senior Research and Development Engineer. Sir has a deep interest and passion in physics and engineering, and he wishes to be a part of photonics revolution, using light to solve world's problems and make it a better place to live in. Today, Sir will be sharing his knowledge on the topic compact, cost-effective, and portable spectroscopy solutions for healthcare. Now, I request Dr. Shuvan to deliver his talk. Sairam.
Shravan, we are not able to hear you. Just a minute.
Can you hear me now?
Just a minute.
We are able to hear this.
Okay, so online you can hear basically.
Gauri sir, we are able to hear him. Only I think inside the MMLC there is a problem.
Okay. Yeah, you can start. Sorry.
You can immediately rectify that.
Okay, sir. So I'll continue then. Yeah, so it is first of all a very humbling experience to be a part of this esteemed webinar where all the greats are presenting something related to healthcare and diagnostics, and with the platform being physics. And I'm sure the talks have energized all of us, and I hope it makes everyone very interested in healthcare as well as diagnostics, because given the nature of pandemic and everything which has started recently, healthcare has become a huge industry by itself, and it is not only going to be the mainstay. Also, it is going to determine how we move forward in terms of even economy, because everything is determined by how we cope up with this pandemic. So without further ado, I would like to then start with my presentation. Let me just share my screen. Can you all see the presentation?
Yes,
Okay.
we are able
Okay. Okay, so the title for my talk is Compact, Low-Cost, Portable Spectroscopy for Healthcare. So I got an opportunity of joining the startup in 2018 when I was a research fellow in NUS, and I was working on spectroscopy. What interested me was that we could develop spectroscopic solutions which can then go to a customer, or could be used on the field rather than in the lab. So that was my motivation to join the startup, and I learned a lot when you look at from an academic angle and versus an industry angle, how different the solutions look like, you get that perspective. And this is one of those opportunities, I think, that also changed my outlook and understanding of things, how physics could be a major um, um, marker for transforming any particular industry, because it is such a broad it has such a broad applications, and that you cannot you would be surprised that you don't find something you can apply physics on. So that's the reason I joined the startup. And so here the main idea is our vision. So I'll just go with the overview, wherein I'll just briefly introduce Atonic Systems, why Atonic Systems was started, and then a brief introduction on spectroscopy, just to give you how you can do a visible spectroscopy with our spectrometer. And then colorimetry is the science of measuring color, and how to estimate colors is very important in our day-to-day. And although these topics are very simple, you would have probably learned most of this in your 10th class, but it is interesting how industry applies them every day to give you the products that you use in your hands. Taking a mobile phone, for example, you have plastic appliance. Any electronic appliance has a color on top of it. So all these color-based QC is done by a spectrometer. So colorimetry is a huge field by itself. And then I will delve a little bit into healthcare applications. So first and foremost being dental care, wherein dental care is one of the active projects we are involved in, wherein we are developing a dental shade scanner. So dental restorative surgery is a topic of interest, because many people get teeth replaced. And often what happens is, when you get your tooth replaced, you want to get a replacement which looks similar to your other teeth. And that's a color problem again. So how do you find the right shade for your tooth? That is interesting. And then I'll also just very briefly show you how spectroscopy can be applied for skincare and other diagnostics. And also for plants. Plants is interesting again, because food security is a huge issue in 21st century, wherein we want to know where our food comes from, what is the food quality, and what is the food freshness. And just to tell you how a simple spectrometer can tell you how good a leaf is, can go a long way in determining how good the crop will be at a future date. So and how good your food will be at a future date. So same thing applies to food food freshness. For example, ripe fruits. How do you tell? Generally, it's easiest metric of finding whether fruit is ripe or not is how the color changes, right? So for example, a banana changes from green to yellow, and apple also, when it ripens, when it becomes older, you can see the color change. So every thing around us is made. We actually visualize it with color. So color is a huge a metric to determine how good or bad a substance is. So it's a easiest of metrics, but also very difficult to determine precisely. So the vision for Atonic Systems was it's a 5-year-old company right now, and the vision is to become a world leader in high-end affordable microspectrometers. So it started all with the PhD of my CTO, Sasha, who started out with a project in his PhD wherein he tried to shrink FTIR spectrometer into a micro FTIR spectrometer, wherein he shrunk the size by at least 1,000 times. So with that starting point, there was no looking back. He continued working for 10 years on this. And now we have products which have been translated from lab to something which people can hold in hands. So, when you have something which you can hold in hands, your application, the gamut of applications that you have are enormous. So you can use it for anything on the field with the portability and with also you need to of course ensure that it is cost effective. Otherwise, it doesn't reach a wider audience. So water quality testing, food quality, any kind of quality assurance, if you want, you need spectroscopy, because spectroscopy is easiest way to find whether a particular molecule is present or not. And that's the way you ensure that a particular criteria is satisfied or not. So that is the vision for Atonic systems. So to give a brief overview of spectroscopy, right? So what is electromagnetic spectrum? So it stretches all the way from X-rays and to microwaves. But what we look at or is probably the visible, which is the smallest part of the entire electromagnetic region, which is just 400 to 750 nanometers. And little bit on the left is UV, little bit on the right is infrared, right? So for this talk, I would just concentrate in these three ranges, UV, visible, and infrared. But these ranges are basically considered as optical ranges. Visible is the one which is visible to our eyes, but UV and IR are non-visible. So generally, the detectors for these are, they're all made of silicon or germanium, depending on the wavelengths, or in gas, for example. So these detectors allow us to analyze light coming at it. So now with this understanding, we look further as to what kind of conventional spectrometers we find in lab, right? So spectrometers are just devices which allow you to break down light into its components, and then you measure the different frequencies and you estimate how these different frequencies are distributed, right? So there are three different types. One is a filter-based spectrometer, then you have a diffractive or dispersive spectrometer, and then you have an interference spectrometer. So filter-based spectrometer is probably right now with you when you are using a smartphone, a camera, for example. It has an RGB sensor inside it, which is red, green, and blue filters sitting on a silicon sensor. So that's the easiest way to reproduce color and also to find out what color the scene has, right? So these are filter-based spectrometers. So they just select a certain band and you measure how much light is present in that band. Everything else is rejected. So this gives you a very easy estimation of what light, how much of light is present in how much range of wavelengths, right? So then diffractive or dispersive spectrometers are typically based on separating light by wavelengths. And interference is based on modulating light based on a phase delay and then establishing the relationship between intensity and phase delay, which is typically called an interferogram. And then you recover the spectrum through a mathematical operation. So that is how an interference spectrometer works. I'll just go a little more deeper. So filters, for example, red, green, and blue. You can see the blue filter, the green filter, and the red filter. These are typically used in all kind of color cameras. So even your eyes have red, green, and blue cones, which I'll again tell you a little later. And that's how you perceive color, and that's how color appears to human eyes. So this is the easiest way to tell, okay, we have this much of red, this much of green, and this much of blue. And that's how you say, okay, this is probably the spectrum. But again, this is a 3-channel spectrometer. So if you want a little more precise understanding of what colors are present, you have much more precise filters, which are again called thin film filters, or they are again based on concept of interference. But these interference filters allow you to have very narrow bandwidths, and then you can utilize this interference to get the intensity in a narrow band of light. So for example, what you see here, this is very narrow band, and you can tell very precisely at a particular wavelength how much light is present, right? So, but these filters are again very costly. But colored filters, for example, the RGB, which is on your phone as well, is very cheap. So moving on, there is diffractive and dispersive spectrometers. So diffractive is basically based on grating. So you have some lines ruled on a grating, on a piece of metal, and when you reflect with that, you have higher orders of dispersion because of the periodicity of the lines. So this is the concept of diffraction. You all may know it. And dispersive is generally by using a prism. This was one of the oldest spectrometer known, because Newton used it to find, okay, the white light which we get from the sun is made of few colors. Of course, the oldest spectrometer would be rain droplet, because that's how you see rainbows, right? So that's the understanding of diffractive and dispersive spectrometer. So these basically break up light into different components, and then you can easily measure them spatially as to what is the component of light and how much of it is present. So the problem with this is that it can be very high resolution. It can have good what you call within a narrow bandwidth it works well, but it may be compromised in terms of high bandwidth. If you're looking at high bandwidth applications or light throughput, you will have issues because you lose a lot of light. When you use a diffraction grating, for example, you lose it to different orders. So typically they use a first order, and the zero order contains at least 30% of light. So you lose right away 70% of 30% of light. And yeah, so, and prism generally, because whatever material you use is gonna absorb little bit of light, and that absorption is going to reduce the amount of light received by your detector. So again, these two methods have their own challenges. And the third method is interferometer-based spectrometer. So here, what happens is you have a scanning mirror. So it's a typical Michelson interferometer setup. It can be any other interferometer as well. They have tried different types of interferometers, but just to showcase how a basic concept of interferometer is, we have here a Michelson here, wherein light comes in straight, and then you have a beam splitter, and then you have two different arms. One of the arm is constant, and the other arm is has a moving mirror. So this scanning arm allows you to measure something called as interferogram. So if you look at this, so the interferogram is basically a measure of light intensity versus the displacement of mirror, which is basically increasing the phase in the light. And this phase actually plays the role of modulating the light received at the detector, and that's why you see this. So with this modulation, if you were to do a Fourier transform, you can recover the spectrum back. So this is how typical Fourier transform spectrometers work. And this is the case of a monochromatic radiation. Let's say now we add extra light into this or additional wavelengths, right? So here we have, let's say, three different wavelengths. And now you will have an interferogram which doesn't look like a sinusoid. It will look more like a couple of sinusoids mixed together. And now if you were to take a Fourier transform of that, you would, based on the Fourier transform, you would recover a spectrum which has three different spectral bands in it. So the advantage of interferometer-based spectrometer is that the light throughput is the maximum you can get. As you can see, you receive almost an entirety of light, and you have something called as multiplex advantage. So detector receives all the light. It's just that it doesn't differentiate between wavelengths. It only differentiates the phase. So, and this information is now mathematically converted into spectrum. So this also is known as, nowadays, there's a new term for this called reconstructive spectroscopy. So reconstructive spectroscopy means you are not measuring spectrum, literally. So in other cases, like filter based spectrometers or diffractive or dispersive spectrometers, you are measuring the spectrum, which means every light channel is, every detector channel is measuring a specific part of the spectrum. But here, you are measuring the entirety of light. It's the white light which is falling on it. But because of the phase delay, you can recover the wavelength aspect of it through a mathematical process. So this is the introduction to our spectrometer. So this is where now, if we were to put all these spectrometers on a chart, on a common chart of, say, cost versus performance, right? So filter-based spectrometers are the cheapest because you have just 3 filters or 4 filters define how much information you want, and then you can define those many filters. And so it's most affordable and most portable. So many sensors are generally based on this. And performance-wise, of course, it's the least precise option because you then have only information of the number of filters that you have. That's the information you have on the spectrum. So it's low cost, but it's very useful for simple applications. So then you have dispersive grating. So this is a mainstay of all the spectroscopy done today, because grating spectrometers are easy to make, first of all, and the resolution achieved is very good. And typically you scan the grating to get a higher bandwidth. But the problem with this device is that it is very costly. So grating-based spectrometers, typically any lab-based spectrometer will range from 2,000 to 10,000 US dollars. Here, yeah, it's about, if you were to use for especially color-based measurements, or even like very high accuracy QC, you might read even higher. You might have to even pay higher amount of money. So then the third part is like Fourier transform. So these are FTIR spectrometers. These are very bulky. They are huge. They take up the whole bench space, and they have a huge scanning arm. And the scanning arm determines what resolution you get. And so all these spectrometers are very precise. They are very good for measuring infrared spectra, for example, but they are very costly as well. They typically cost about $50,000. And again, it depends which wavelength range you're looking at. If you were to go towards mid-infrared or even higher ranges, it gets even more costlier because of the detectors. So where does Atonic position itself? So Atonic is making these phase delay lines in a very small form factor. It's like an interferometer built on a chip. So what you're getting is some kind of low-cost alternative for the FTIR, wherein you have large bandwidth, and it is fast because there is no scanning arm, and it's rugged, and it is the smallest form factor. So how does that work? So you basically shrink down your interferometer into a small chip, which has multiple delay lines, which is carved out by X-ray lithography. And this is our patented technology. And this chip then sits on a detector, and then that's how we have our portable spectrometer. So the advantage of this is your spectrometer itself, the module itself, is as big as the chip. The size of this particular device that you see here, this is our latest offering. It's called AtoCube. Is predominantly because we have put in extra LEDs to shine light on anything, and I will give you a demo further down. But yeah, so this is the spectroscopy is literally on a chip. So that is the biggest advantage, and there are no moving parts. It's all a static device, and you get high spectral resolution because it's an interferometer after all. And when you use a grating, for example, or a prism, as soon as you start reducing dimensions, you start losing resolution, because you cannot draw two fine lines, right, on a grating, for example. And prism, when you start shrinking the prism, your dispersion becomes much lesser. And so because of that, you cannot really get a very high resolution when you shrink the size. So that's the advantage of getting an interferometer on a chip, wherein you get best resolution at low cost. And these chips are made at wafer levels, so you can get at least 100 to 200 chips on a typical 4-inch wafer. So that's the advantage of Atonics. So this was pioneered by my CTO, Sasha, who worked on this for like almost his 15 years of his life. And finally, this product has come from lab to the market. So there's just to give all students understanding, always when you do things in a lab, when you do something in your PhD, what you're doing is cutting edge or frontier research. But when you want to translate that to common man, it takes a lot of effort to make it simpler, make it easier, make it more scalable, and make it cost effective. So it takes a lot of time to come through all this and then make a product out of it. So that's the usual what you call as roadmap from technology which is in a lab to technology which is in the industry and to the common man. So that being said, so we are trying to get something which can fit our pockets. So just to show you how the chip looks like on a CMOS, this is how the chip looks like. And when you scan the wavelengths across, you get a different interferogram every time. And when you convert it back, you get a monochromatic spectrum. So this is a typical monochromatic spectrum from our device. And so talking about miniaturization is a huge topic in spectral sensing nowadays, because spectrometers are always seen as bulky devices. And these devices are, if they were to be made portable, they can be used for different applications, and they can be used to do QC on the go. So the whole part here is because of high costs associated with spectroscopy, many people don't use the spectroscopy for QC. They use much more simpler QC methods because they are fast and reliable. But spectroscopy can give edge over the precision or accuracy of your QC, which other methods cannot give. And so the drive is towards miniaturization. So as I said, if you look at miniaturization as well, there are lots of different techniques tried over the past few years. This is a image from a review paper which recently came out, in which again they describe it into similar kind of sectioning, which I told you how you differentiate between different technologies. So you have dispersive optics, narrowband filters. Then they separate, of course, the Fourier transform and the reconstructive spectroscopy. So ours is kind of at the bridge of these two, or the cusp of these two, wherein we use interferometer as well as reconstructive spectroscopy. So, so presenting our device, which is the AtoCube, it just fits the palm. So I have one here with me, and so the wavelength range is from 380 to 1000 nanometers, and the optical resolution achievable with this is 12 nanometers. Repeatability, which is useful for finding, say, atomic lines, or even the laser lines, is very high because we are using an interferometer at the base of it. So this is literally spectroscopy from lab to pocket. So this can really fit a pocket. So the example applications where this kind of tool can be used is multifold. So if you look at it, you have color measurement, you have food freshness and quality. How can you measure freshness of vegetables? So imagine a person using this daily to see whether his salad is fresh or not, or whether his food is adulterated or not. So imagine what all applications can come through that. Then lighting measurement. A lot of even production of video production units, they use lighting measurement tools to establish, okay, this is the light I have on the scene, and this is how I will change my exposure. And so for LED manufacturing, for outlets wherein they, which are selling, for example, clothes or apparels, right? You want to have the best kind of lighting so that people can distinguish colors. It might have, you might have noticed that when you go to an outlet where there is low light, you will not be able to distinguish between certain shades of blue or certain shades of green because of the light that is falling on the apparel. So that itself is a science in itself. So light measurement is a huge topic. Then counterfeit detection. Then semicon industry also uses spectroscopy to measure their processes. How plasma, for example, plasma etching is a process which is used for etching wafers, and to find the end point of a particular process, they use spectroscopy. It's called optical emission spectroscopy. Then you have skincare. Skincare is again finding what color your skin is or how good the health of your skin is. You can determine by finding the molecule of your choice. So melanin, for example, is responsible for how what your color is. And then moisture tells you how good the skin's moisture content is. If you have not drunk enough water, for example, your skin starts showing the signs of low moisture. So this is one way of finding whether you have also some kind of skin cancer. So there are multiple applications in skin. Then hair care. Hair care is a huge industry. So for example, when you color your hair, how do you know which color will you get? Especially in fashion industry, or celebrities, when they color their hair, they need to know exactly what color it will result in. And because of bleaching or coloring your hair also undergoes a lot of damage. And this damage can be established by looking at the spectrum of the hair. So, and agri-tech is again based on determination of plant health, and for example, soil analysis. Then academia and research, there are lots of general spectroscopy applications which academia is interested in. So these are like a huge number of applications. So it's like you have a hammer, and these are all different nails that we can hammer them on. So that's why spectroscopy, or in general, even physics, has huge number of applications. So, and in addition to this, we also offer something called as AtoCore. So this is just our MPA chip and a CMOS detector. So this is something which we offer it to our OEM customers who can then integrate it into their devices. So moving forward, so this is our software, and this is like any other spectroscopy software, and it's used for measuring the spectrum. You get the spectrum chart here, and then we have a color chart as well. I will also give you a small demo on color measurement with my device. So just to show you how it works. And just to give that demo, I need to just brush up your basics on spectroscopy. So spectroscopy is nothing but measuring color, or measuring wavelengths, intensity versus wavelength, which is a spectrum. And you have typical spectrum measurement is just directly measuring the light source. Reflectance is measuring the reflectance of a surface, and transmission is with some sample in between, and you measure what is the transmittance of that sample, right? So for reflectance, typically you measure dark spectrum, then you also measure the spectrum of the light source, which is known as the bright spectrum, and then you get your reflectance by dividing spectrum over bright your measured spectrum over bright spectrum. So that is the reflectance. So color measurement is basically, again, it's a huge field in itself. So I'm putting it very briefly here. So the whole science of color is to understand how our eyes perceive color. So our eyes actually have three different cones, which are sensitive to three different bands of light, which is red, green, and blue. And that these cones are responsible for measuring the colors, and then our brain puts it together to say, okay, this is the color yellow, this is the color blue. And this took a while, and there were so many standards which came in between how to understand or perceive color and how to communicate it. So typically what is done is, to give a short intro, you take a reflectance of a device and of a surface, and then you multiply it with an illuminant, and then you multiply with the measured functions of these cone responses, and that's how you recover X, Y, Z. So these X, Y, Z parameters are called tristimulus parameters, and these are the chromaticity indices, literally, which is telling how much of light is seen by each cone of your eye. And this XYZ can then be further converted to RGB, which we all know how an RGB works. So all your screens that you're watching this presentation on are RGB screens. So RGB is very simplified version of how your eye perceives it in terms of measuring R, G, and B in 0 to 255 levels, right? So that's RGB. So it's a very what you call basic understanding of how light measures something. And the same RGB is again used in a color camera, wherein it sees R, G, and B, different intensities of R, G, and B, and then puts together a scene which is colored. So that's how color science works. So this is a typical color chart which is used for doing QC. So just to show you how a device works, so you see that every color here, so one is gray tile, you have some kind of response which looks like a broad white reflectance. So it reflects everything like a white, whereas blue, for example, will only reflect blue, green will reflect green, red will reflect red part of the spectrum. So that's how color works. So when you see red, you still have some more computation to go from spectrum to this color which is presented on the screen. So let me show you how that works with a simple demo. I hope you can see the screen here.
Yes, sir.
Yeah, okay. So this is our spectroscopy software, which is called AtoView. And if you can see my camera, let me just put this here. So this is the same chart that I showed you just before here, right? And this is our device. So the device has LEDs built into it, and I can show you. You can see the LEDs glowing here. Can you see it? And So right now I'm trying to measure light from this color chart. So I have light falling from the spectrometer on this, and what I measure is the light coming off from the surface. So there's a spectrometer at the end of this device at this point, and you have LEDs built into this part. And all along you have optics which convey the light back to the spectrometer, right? So you can see here different colors. You can see how they show up on the right side of the screen, right? So that's how a typical color-based spectrometer works. So you have a spectrum. So spectrum looks like this. And a white spectrum is basically the light of the spectrum of the light, which is from a white surface. So this is how I have LEDs, which are white LEDs. So this is how they look like. And when you put it on any colored surface, so this is red, for example, or yellow, this is how it looks. So you can see on the left side, the spectral plot. On the right side, you see the color. And the same thing, if you were to see the reflectance, then it's based on how much is reflected back based on the white light. So white light would be somewhat like 100% line. And then if you look at blue, green, red, you see each reflecting different parts of spectrum. So that's a very brief presentation on the color. And also, of course, you can measure the skin color or hair color. So hair color is, I don't have much hair left now, but yeah, so this is very handy. It can fit the hand of any person, and then he can put it anywhere he wants. So this is basic presentation of our device. Let me now come back to the PPT and show you just a few applications. Okay, I hope you can see the yeah. So we had a quick demo. So now we come back again to something which is more interesting. These are applications which are used for day-to-day needs, right? So this is dental shade scanner. So we got this project because there was a problem in aesthetics of dentistry. So aesthetics is a huge field in dentistry wherein you try to restore teeth. And when you restore teeth, the problem always is if a person has a tooth replacement, he always, the dentist finds it hard to find a tooth which has the right shade, which is matching the other teeth in his mouth. So it's a huge industry because every tooth restoration in India, I checked up with a dentist, it costs around 20,000 rupees per tooth. And what happens typically is that a dentist you pay a visit to the dentist, you ask him for a change of tooth, and he measures your tooth, typically with a shade chart, which is seen here. And the shade chart tells you, okay, this is roughly here, based on you put the shade chart against the tooth, and you try to visually tell what is the shade of your tooth. But what often happens is when this goes to the clinician who makes the tooth with materials like ceramic, with zirconia, he puts together a tooth which probably has slightly different color or shade. And when you put it back on the on your teeth profile, you would see that this shade doesn't match. And it's a huge problem because what happens is when any person goes to a dentist, he has to visit at least twice or thrice just to get the color shade right. Now, if we were to solve this problem, how would we do it? So we need a measurement device which can measure the shade of the tooth, and the dentist needs to have it, and the clinician needs to have it. So there's a huge problem with color communication between dentist and clinician because the shade chart looks different in the different colors, different lighting. So if the dentist were to measure your tooth with the shade chart on a rainy day versus when on a sunny day, he will have a very different shade selection. So whereas that problem of shade selection is eliminated once you have a spectrometer, because that will measure it precisely. It will give you a more accurate measurement of tooth. So that's why we went on this project, and it was a very useful application wherein we could make a difference in terms of the problem is really huge, and this fits very well with our colorimetry, because we are trying to establish how to measure colors. But in this case, the solution space is in kind of measuring colors for teeth, right? So you have so what does this dental shade scanner comprise of? It has a diffuse reflectance probe with built-in LEDs and a spectrometer. So you typically, it's our usual spectrometer core, which we also call as AtoCore, and then you have a reflectance probe here. And you can see our CTO measuring this shade chart, for example. So what happens behind the scene? So you have LEDs coming through, lighting up the fibers, which are then used for lighting of the tooth. So the same thing as what you saw here, wherein I showed you how a spectrometer converts spectrum into color. It shines white light and it receives the reflected spectrum and it converts it into color. Same thing is done here, except that teeth are like 4 mm by 4 mm. It's not really huge. So you need to have a smaller probe. So the way to confine light into a smaller space would be to use a fiber. So that's why we have a reflectance probe made of fibers. We have a collection from the central portion, and you have fibers which are lighting up the edges. And generally, tooth is a very hard material to understand, because tooth is made of two things. One is enamel and dentin. So you can see that any kind of translucent material always scatters light within the material itself. There's a light scattering within the material. So that's why the tooth color is not just the color on the surface, it's a whole tooth itself. So it's again a very big topic in itself, and there are lots of publications on this to establish how to get the right shade match. And it changes with material to material. So if you were to do this with now zirconia, or you did with ceramics, you will get very different results, because very different spectra, because both are different materials and they scatter light differently. So this is a typical measurement of the shade chart, and you can see here. So we have measured LAB. LAB is again a measurement standard recommended by CIE, which is the authority on colors. And LAB are just like RGB. Think of RGB in a different coordinate system. So LAB values for the 5 of the shades. If you look at it, so our spectrometer has very less error in estimating these shades, and you can see the precision of it. So typically, you can see the main thing. The main problem with teeth also is that it's not just color. It's just probably just a very small color space. In the color space, it's like within white to yellow spectrum, right? So it's very precise. Very precise shade would be hard to obtain. So moving forward, just for giving you some more applications for skincare, we can do, as I said, skin tone measurement, effectiveness of sunscreen, for example, if you apply a sunscreen, do you get UV protection or not? And whether you have if you have an allergic reaction, can you measure based on your skin color? Then moisture in your skin also gives a lot of information of the health of your skin. And skin melanoma is a huge topic. Again, it's then oxygen concentration, and um, even heartbeat, for example, you can actually measure if you put the spectrometer on your skin. So just to show you a very simple demo, so this is a measurement of heartbeat from our spectrometer. So we just measure the light coming back from the finger, and if you analyze it and put a Fourier transform on it, because it's a temporal scan, you can get the heartbeat of the spectrum, heartbeat of the of your temporal intensity. So you look at the intensity of blood. Blood is generally reddish, so you have around 600 nanometer peak. So you measure the intensity of that over time, and then you take a Fourier transform. This is a very easy way of showing how your typical health bands measure your heartbeat, right? So this is just a showcase. So the same way you can also measure the blood deoxygenation and oxygenation. This is very interesting because this was used a lot for determining whether patients had enough oxygen in their blood for COVID diagnosis, whether a COVID patient had lung failure. The only way to determine that is using a pulse oximetry. So we also thought, okay, let's try it out with our spectrometer. So what we did is we put a rubber band on one of the fingers, so that stops the blood flow. So because of that, what you see is the blood is having lesser oxygen, and you can see that the oxygen level starts dropping as soon as you start measuring after this. And at some point, we break the rubber band, and you would see that the oxygen measurement will go up. So this is the hemoglobin with oxygen. So at some point, it will break, and at this point, you start seeing there's a peak of oxygen going up. So this is again a very simplistic demonstration of how you can use these kind of spectrometers to do everything at home, and you can use it for different purposes, get different metrics, and it's a healthcare diagnostic device. So, and plant health diagnostics, I'll just give a very brief intro. So plant health is, again, if you have a leaf or something, you can tell based on the color of the leaf as well, how good a leaf is. So generally, I just got 3 leaves here to showcase. So for example, a good leaf will have higher chlorophyll content, little worse will have lower chlorophyll content, and the worst will be something which has no chlorophyll. So chlorophyll is again a huge marker, is a big marker for determining how good a plant is, and that helps people determine if the plant will survive or not, and also tell what kind of stress it is under. So so chlorophyll leaf fluorescence is again easy way to determine. So we had done some studies on this, but I'm not presenting it here, but wherein we can see that when you bleach the chlorophyll and then you let it decay after that, and you again check the fluorescence, what happens is the leaf recovers back at some point. So the recovery rate, if it is good, that means the leaf is fresh. If the recovery rate is bad, that means the leaf doesn't have enough chlorophyll, and that's why it is failing. So there are ways to put these metrics into action and to find whether your crop is going good or not. And so just to tell about our team, so it's not just a single person on this whole project. I've shared the work of all of our team here. So we have 2 founders, Sasha and Philip, and then we are supported by many other people. So Prof. Moser is the brainchild or had the brainchild of this spectrometer, and he was the PhD supervisor of Sasha. And then we have other team members who work on different aspects of it, from manufacturing to product development to data analytics. And I'm a physicist, and I I am involved in different stages of this in different roles. So I'm kind of a jack of all trades, and I see myself in developing this product further with the team, and I enjoy it thoroughly. Thank you so much for your time, and I'm open for questions if you have.
Sairam,
Sairam, sir.
Sairam, Dr.
Sairam.
Prashant, it was definitely very wonderful to hear you, to see that sea change that has happened in the transition of use of spectrometers.
Exactly,
Almost
yeah.
3 orders of reduction and just
Yes.
a handheld unit. And say, in your own words, you have said from lab to pocket, which is just a wonderful thing to have. In one of your slides, you mentioned that there is definitely a reliability, or rather reproducibility is there.
Right.
My question to you is, you also mentioned, say, for example, when you're talking about the dental part, that
Yes.
the color changes, or rather, we perceive in a different way when we see on a sunny day and on a rainy day.
Yes.
That is the visual perception.
Correct.
So in such condition, how do you say that your unit will have a reliability on the data accumulated or captured?
Yes, so yeah, we are working actively on it, and we also are presented with these challenges because so one thing for sure is the reason spectrometer works the way it works is it has its own light source, and we measure the reflectance based on the light source. So you are as good as you measure the light source. So the accuracy is then based on how accurately your spectrometer prints out the data from the reflectance. But reflectance is not enough here. So what happens here is if, yeah, as you said, the ambient conditions can play a role. So
Yeah,
for
that's
that,
very important because we are used to using Perkin-Elmers and so on. The cavity is closed, so there is a controlled exposure of light to the object. While here we are keeping it at ambient situation. So there will be interaction from outside. How do you control that? Or have you taken, maybe you have taken care, but what I meant is today I do a measurement at 10 o'clock. My same measurement at 4 o'clock may vary on the same sample.
Correct. Yeah. So what happens here is when we measure it, so one thing we ensure is that we take care of the dark spectrum, as I said in the beginning. So dark spectrum is not just detector electronic noise, it also involves the scattering noise which is present. So you remove the dark spectrum, and then so that makes the measurement a bit more absolute in that regard. It takes care of the ambient conditions when you're measuring it, and also there are other smaller changes that we also take care of. For example, if you were to use this tool, you can use it in a little without a direct overhead light, for example. So and we found because the light source is right on the tip of the probe, you don't have much loss. So you basically recover the light coming from the probe rather than any other light, because that light from the probe is the strongest. So you don't see any other light coming there. So, and your oral cavity itself, so if you were to measure this on tooth of somebody, oral cavity itself acts like a dark cavity. So it helps in that way because you're measuring against the tooth, and you try to put the tooth scanner, and at the background you have a black background. So that's how we take care of it. And there are definitely challenges, but not something which is impossible to circumvent. Yeah.
That's one more question. Now your unit, as I see it, basically I would put it like that, it is very good for what we call the analytical measuring tool, colorimetry.
Right.
Yeah. And so do you think you recommend that today the colorimetry, which is a wet analysis, can be replaced by your unit?
Yes, yes. So in fact, I've not presented.
Can we recommend it as an analytical tool for college level?
Yes, I think so. I mean, right now the way we are marketing this is more to do with day-to-day needs of spectroscopy, but it can become more accurate if you were to have a little more precise, a better detector with more control over it. So it becomes a little more bigger then. But again, if you want to use for day-to-day measurements, just want to check how the sample is, you can still get very accurate results with it. It's just that uh, at some point your cost versus efficiency, right? You have to draw the line. So what exactly you want to do, then you have to specify, and then based on that, we can check whether it measures it or not. For example, if you were to use something like a PMT and a monochromator for doing spectroscopy for analytical work, that may not translate directly to this device, because this device is something which is meant to do portable readouts, and the sensor here is a silicon sensor, which is not at the same level as a PMT. So that's why the challenge is always between the cost and the portability of the application. And if you want to include precision, you can go up to a certain level. You cannot push the limit beyond certain limit. So analytically, I would say for colorimetry, it can be done. For fluorescence, sometimes this may be a challenge. And for colorimetry, actually, we are working with few groups wherein they have analytes which change color because of a reaction, and then we measure the color change for them. So we have done those kind of studies. We have also done, for example, chlorine bleaching measurement. How much chlorine, for example, they use chlorine to clean the pools. So if you want to know how clean the pool water is, how do you know? Generally, the way they do it is they add a particular chemical, and the chemical changes color. So it's any litmus test, for example, is based on a change of color. But now, if you were to use a colorimetric sensor, you can get very precise change of color, and then you can say, you can put a better number of concentration of your molecule or analyte, and then say this is the right color, or this is the right concentration I want to measure. Yeah.
Thank you.
Thank you. Thank you. Regarding other questions, so Manoj has asked how color value is obtained from spectrum. So spectrum, as I said, becomes reflectance, and then is converted to XYZ coordinates, and then to RGB or LAB. And Akhil has asked what type of LEDs have been used. The LEDs are generally white LEDs. So white LEDs have actually, there's no coherence, actually. These are incoherent sources. So, and so peacock feather pigment is brown in color, but it shows different colors due to the structure. Will the spectrometer be able to determine these differences? So spectrometer generally is measuring a composite color. So it may not be able to see these differences. It depends on how far you're looking at it or how close you are. And the angle and the way you collect light, it's the same way how you look at peacock feather, right? So the angle of light which is incoming will change your perceivance of the perception of the color. Then does the output of the device change in case of sunlight and in artificial light? No, it doesn't, because I mean, you can use this for measuring the light source itself. And the way we measure it is we always measure it where it blocks the light from outside. So it is completely blocked. And that's how you ensure that there is no external light when you're measuring it. Then how accurate are the results of the Atonic spectrometer? So I showed you the results for a typical color metric chart, in which so the red and the blue line. So the blue line is a typical grating-based spectrometer called, we have taken auto, and this is how our spectroscopy measurements look like. So this is for the different colors, and you can see here. So it is not used for IR and UV right now because our the manufacturing, the way we have done it, is meant for visible, and it extends to near infrared. So it is more or less limited by our sensor, which is from 380 to 1020. So then I think, yeah, so interference has, so in this case, right, so interference is the nature, here you're not using a laser for interference, so it's not related to that. It's not related to the coherence length of LEDs. So you are using, you are measuring how the light passes through the structure, and then you're measuring what is the output of that structure, and then you're translating it back to a spectrum. So the structure itself produces a change, as you saw. Yeah. Over the prolonged period of time, the performance of the detector may start to degrade. Yeah, so generally the performance of detector, as far as we have seen, it doesn't degrade so much right now. I mean, we don't see the degradation on the detector itself. What we see is on the LEDs. So LEDs have a typical shelf life of 10,000 hours or something. So after that number of hours, it starts decaying. So generally, I mean, so far we have not seen, yeah, some kind. We have not seen a degradation in the output. That's it.
Sairam, sir, I'm
Sure.
sure there will be a lot more questions, but due to shortage of time, we will take the other questions later. So I
Okay.
thank you, Dr. Shubhan, for your wonderful talk. And I'm very thankful to you for taking out your valuable time and being with us today, sharing your knowledge and experience with all of us. Thank you very much, sir.
Om Shri Sairam, offering myself at Swami's lotus feet. Sairam to one and all present here, both physically and virtually. I have a pleasant duty today to introduce Dr. Anshuman Jyoti Das. Dr. Anshuman is the co-founder of a startup, Labby Inc., a startup born at MIT Media Lab that is developing breakthrough mobile spectrometer technologies for industrial applications. Sir has done his BSc Honours and MSc Physics from Sri Satyasai Institute of Higher Learning and went on to pursue his MTech in Lasers and Electro-Optics from DIAT Pune. Sir has done his research from Jawaharlal Nehru Center for Advanced Scientific Research, Bengaluru, on the topic Organic Solar Cells, Light Harvesting, Large Area Devices and Stability. Previously, Sir was a research scientist at MIT, Media Lab and MIT Tata Center for Technology and Design. Sir has 3 patents to his name: methods and apparatus for imaging and 3D shape reconstruction, mobile device-based fluid testing apparatus, an organic solar cell and methods thereof. Sir has extensively worked on polymer optics during his PhD, and later he has worked on smartphone-based skin imaging, food sensing, designing smart biomedical devices, and paleontology. Now, I invite Sir to share his knowledge on the topic Computational Imaging, Quest for Superhuman Vision. Sir.
All right. I think I'm audible, I guess. Thank you, organizers, Gauri sir and Deepa ma'am, for the opportunity. Greetings from Boston. It's always a pleasure to be back and connect with the with my old physics department, and it's definitely a very enriching experience to hopefully interact with the current students across all the campuses. I'm going to just see if I can present. All right. All right. I think you should be able to see my screen. If anyone cannot, please please send me a chat or something. All right. So the topic is computational photography towards superhuman vision. The superhuman vision part is just a fancy title. Pretty much all the talks in this in this webinar are doing some kind of superhuman vision, like something that we cannot see, that have limitation, that our eyes are limited, and we need external help from technology to see. Just to put something the talk in perspective, I'm taking a pedagogical approach to this topic. The first half, I think I'd like to go to the basics and gradually build to my research, and only in the second half I'll share some results from some of my research in healthcare. And the goal is to not overburden you with a lot of results and a lot of jargon, but to keep the concepts a little bit simple so that you have some take-home message at the end of it. So all of us do use cameras for taking selfies, to either doing research or to capturing our lives. And there's something that's common when we look at photography or imaging is you need a scene. There's something that you're capturing. You need some device to capture. I'll call it some kind of a sensor that has some either some optics, maybe a lens or two, some kind of lighting. Either it's controlled or it's not. If you're outdoors, you're pretty much relying on the lighting from the sun. And then you need modern photography or imaging is incomplete without some kind of post-processing, whether it's you're doing some kind of image processing at this stage or something more complicated like machine learning or artificial intelligence. If you look at it, our vision is very similar. I mean, we've built technology that kind of mimics the way we see things, and so the lens of our eyes and the cornea are behaving like the focusing elements. Our retina is like the sensor of the camera, like a CMOS sensor. Our brain is doing all the interpretation. We're seeing the images, and unfortunately, we do not have our own lights. Our eyes are not like shining some lasers or stuff, so we are limited by external sources of light. So that's kind of the parallel. But I mean, our eyes are amazing, and our vision system is super complicated, and it's a marvel. But we do have limitations, and all of the research in this conference is kind of based on how can we improve that. How do we improve the spectral range? How do we improve the speed of what we can see? How do we improve on the dynamic range? Can we operate in a hazardous environment? Can we measure and see depth, increase our field of view, and things like that? So the goal of all of the research that I work on, and most of the presenters are working on, is trying to see how we can beat our own eyes. So that's pretty much what superhuman vision is. In a conventional photography setup, you try to improve or achieve the image predominantly using optical components or optical processes. For instance, I want to see better, I use a high resolution sensor. I want to see farther, I use a zoom lens and things like that. In a computational setting, I'm trying to augment or improve upon the functionality of the imaging using a combination of some kind of computation. So it's not just image processing or some kind of software. I'm trying to see if I were to go back and look at the scene here, what all can I control that that will improve the capabilities of the imaging or the method dramatically? Can I control the lighting in a computationally controlled way? Can I change the sensor to capture depth, not just a 2D image, and things like that? So it's generally a combination of some kind of hardware, but not necessarily an optical hardware. So that I'd like to clarify. And the benefit of that doing that is, in many cases, we can achieve a superior performance from these imaging systems without the added cost of optics. Lenses and filters and spectrometers and all of these other components are anything to do with the physical hardware is expensive. And if you have some high fidelity coatings and things like that, it just dramatically increases the cost. The goal of computational methods is to kind of arrest the cost by compensating for it in somehow in computation or software. And with some hardware that's not necessarily doing some optical processes. Okay, let's start with a very simple image. It's an array of coordinates, and each coordinate has some value, right? If it's a binary value, it's a 0 or a 1, or it's a white or black, I end up with a QR code or a barcode, just like a black and white image. If I would add color to it, then I would have pretty much a very high-dimensional array where there are 3 matrices for each pixel or each coordinate that correspond to the color. And so here you can see in this case, you can actually deconstruct a color image into its components. If I were to add color and time, you would pretty much get a video, right? So this is basic photography, simple. You're able to get, you're able to digitize what you're getting, and you're able to look at the, get a video, right? But what if we want to see more than that? Because we want to see more, because in medicine, we want to see inside our bodies, right? We want better navigation, like we're talking about self-driving cars, you're looking at intelligence that is scanning the environment, whether it's manufacturing, automobile, aviation, and research in general. We want to see more than our eyes can capture, right? So in those situations, let's put a constraint on this time. Let it not just be the normal time that you capture video on using a video camera. Can we go down to milliseconds, microseconds, nano, or even femtoseconds, right? What new information would come out if I were to capture images with this with an additional time resolution? Our eyes are looking at things around 15, 20 frames per second. And a fast camera, a very expensive camera, could go up to 10,000 frames per second. And if you are fans of the Mythbusters, like you're looking at, for instance, just 73,000 frames per second. What you can get from all of these is, let me just mute this. You're able to see aerodynamics and some of these physics that we would not be able to see. So it's opening up new avenues of research. It's expanding our horizons on what is that physics that's happening at those time scales, right? So that's just by looking at capturing images faster. Now, in this case, you do find like these cameras are super expensive. but it's the trade-off between how much extra knowledge you can gather for that cost. Just another example from my lab back at MIT. Some of my colleagues were able to convert a streak camera. I think most of you are familiar with what a streak camera is. It's typically used in ultra-fast spectroscopy and to look at very fast molecular processes. And they were able to convert it into a two-dimensional a camera that could take 2D images. And at that, we're talking about a trillion frames per second that could be possible, with the streak camera. It's very, very expensive, probably $1 million camera, but this is a reconstruction of a pulse of light actually traveling through this bottle as the camera would see it. You're talking about slowing down the light by 1 trillion times, because if you look at the speed of light, it's 10 to the 8 meters per second. Yeah, and if you look at the speed of the camera, it's faster than that. So again, it opens up. It actually opened up a new field where researchers could start looking at other things, like what happens as a pulse of light bounces off a tomato. You can see, for example, in this reconstruction, a lot of subsurface scattering that's happening. Some of the light that's been trapped inside cavities and things like that. So again, it's opening up opportunities for us to see things that are way beyond what our eyes can capture. Okay, let's look at what if we were to capture delta t, or like the time difference between two images. So if I know the speed of light, what I can do is calculate depth, because delta t would be directly related to that. In most practical scenarios, we generally use some kind of frequency modulation and measure the phase difference, but the principle is similar. If you can do depth now, that opens up again so many opportunities for just from scanning, for design, for manufacturing, and in today's times, the devices that you can use for doing depth imaging are pretty much commodity, from the Kinect, the Microsoft Kinect that some of you would use for gaming, to many other dual camera kind of like stereo camera setups that you could also capture depth. I would, and for instance, in this, I would call this as a time of flight technique, where I'm not only capturing the usual components of an image, which would be the intensity and the color, but I'm also able to capture the depth by looking at time differences that are coming from the surface. I'll leave this for your follow-up if someone is interested how basically a Microsoft Kinect 3D scanner works, where each pixel can also capture depth. So that's and so this is one example from some of my research. We kind of adapted that because it is $100 gaming device, and if there was some way for me to capture the raw data coming out of the device, I could probably start exploring applications where the cost and the size or the volume of the measurement would be a limitation. And we found that museums were very enthusiastic about this. So they invited us. So this is me at the Field Museum of Natural History in Chicago. If you haven't been there, definitely worth a visit. And this is the skull of one of the most famous exhibits that they have. It's a T-Rex skull. The name of the exhibit is called Sue. And we were able to pretty much scan the length of the skull is like 2 meters, and with some kind of optimization, we were able to scan the entire skull in less than 5 minutes for maybe $100 worth of equipment with some decent resolution. Pretty good, actually, not bad. And you can see some of the reconstructions of the skull. So again, having an added metric such as delta T to your image can open up more opportunities. And probably a quick video before we go to the healthcare applications. The same setup that we saw with the streak camera, if you were to now start capturing depth information, because the camera can distinguish between two images that are separated in time, what our group was able to do was use this information to look at non-line of sight images or reconstruct scenes that our eyes cannot see directly. In fact, there is a wall in between this mannequin and the camera. There's no direct line of sight. So this is pushing the limits of how we can manipulate light or the information that's coming from the scene to go beyond line of sight. This is it's amazing. So in this case, what if I were to simply summarize this, what if I could put my eye on a wall and the wall is able to see some get a very different view of things. So it's basically taking my eye and putting it on something far away from me to see what what the wall is seeing. So that was like pushing the limits of what can be done. All right, so now I move on to like more of what my research is and some of the healthcare applications. So we looked at color, we looked at time, we looked at delta T, which was pretty much depth. What if I could measure phase? And so in phase, I'd like to clarify here. The phase, when I'm doing phase modulation here, if you recollect the first slide, we spoke about a sensor, a scene, the lighting, and the post-processing. I'm talking about more towards the lighting. So can I use computation and modulate the lighting itself to see if I can gather more information? Because our eyes definitely cannot do that. We just don't have our own light source. So this technique is called structured light. It's very well known, very well established industry technique. And the concept is actually quite simple. If I had this pattern of, like, say, sinusoidal pattern, which I could use a projector to just generate, and then I could be this. I could just put it on my face. Depending on the profile or the profile of my face, my nose, my mouth, etc., you would see these contour-like patterns. And at each point where there is a discontinuity or some kind of a profile or a relief pattern, you would see a phase change that can be captured using the camera. Although you cannot just use one single pattern to do it, and I'll tell you why. So this is some of the basics of it. At the end of it is some simple trigonometry and trying to solve a set of linear equations to arrive at the depth. So here you can see from this relationship that the z here, or the depth, I would call the depth, is geometrically related to the phase difference, phi minus some phi naught. And if I can determine that phase difference, or just the phase, I can actually get the z, or the depth here. So that's the goal here. So just some simple equations to keep in mind. The intensity that the camera would capture would be some kind of a sinusoidal pattern. Here it's like some cos function. There is a phase pattern. There's some kind of there are it's a spatial, it's a 2D pattern, so they're going to be X and Y spatial frequencies. Some kind of a DC background component, and some kind of modulation. That's or you could just have some varying pattern that's represented by B. So the goal here is to solve for phi, because I showed in the previous slide, phi is related to this depth. Just doing some simple trigonometry. So how can I do that? I could just shine or illuminate 3, 5, 7 patterns which are slightly shifted. So when I say shifted, it could be some kind of adding some kind of like a shift here, like a phase shift. And when I try to do the math, I can actually, so the I1, I2, I3 is what the camera is capturing. And I'm trying to, I know what the phase differences are here because I am controlling that in my lighting. So I can pretty much solve for the phi here and get the depth information. So here, this would be like some of the other details. So here, this is a typical fringe sequence as we call it, a projection sequence. So all of these 5 images have slightly shifted, spatially shifted fringe patterns. And I can then capture these images, do some segmenting, because you want to kind of cut off the regions where there are no fringe patterns, because they would add noise. Do some kind of phase unwrapping, and then you can get back, you can extract the depth information. So let's look at an example now. We were just randomly talking to some physicians in the who are ENT surgeons, and they mentioned about, can we measure the depth profile of our eardrum? This is our ear. If you see this is our outer ear. As we go inside, this section is the middle ear, where you see the eardrum. There are some bones here that connect it to the inner ear, and that connects it to your brain. So as there is, our eardrums receive a sound wave, it vibrates, and those vibrations are converted into neural signals. The eardrum is a very, very peculiar component of our bodies. It's a very, very thin membrane, translucent, and it has got a slight curvature. And so let's look at probably a cross section. Yeah, you can see this. That's kind of the eardrum. It's about a centimeter wide, and it's got like a slight curvature here. So we're looking at trying to measure depths in the range of few millimeters if you have to capture this. And the interesting medical condition that we are trying to capture in this is middle ear infections. So as you can see in this image here, behind the eardrum, there's actually space, and this is by design, because the eardrum needs to vibrate freely. So there's actually air there, and all of that air, the pressure there is actually it's equalized the rest of your face, like the nose, the mouth, and all of that is at the same pressure. When there are infections, and we see that in children quite a lot, and when you have a cold, what happens is this tube that connects the ear, the middle ear, this cavity, to the rest of the, to the throat, actually, it gets blocked. And that's what you feel, this stuffiness in your ear, because the pressure inside is not the same outside. And that actually can encourage bacteria to grow, and there can be fluid secretions. And eventually what can happen is, so this is the normal ear. It's there's just air there. You can have fluid buildup, which can push the eardrum, and the eardrum is flexible, supposed to vibrate, and it can deform it. And so the physicians were asking us if we can detect these bulges. And there are other situations where a negative pressure difference can make the eardrums even it can get kind of pulled back or pretty much opposite of the bulge. So all of these small pressure differences have some kind of diagnostic value, and so the goal was to try to see if we can measure that. So this is an otoscope, which is a device you would see in most your doctor's clinics, and we set out to make this a 3D imaging enabled device. This device has been there since like 1800s and it's never been changed. So it was a good opportunity to try to see what we could do. So we ended up modifying the device. So here, as you see, there is a projector because we want to do the phase modulation and we want to control it through the lighting, right? So we have that. There is some focusing optics here, and then there is a reflected light goes through. We just had a simple webcam, and that's connected to our laptop to do the image process. This would be like a rendering. You can see some of these initial tests that we did on some ear phantoms. And these are the images. So this is like a phantom. It kind of mimics an eardrum before we actually do it on patients. And you can see there is like, as we pump air or suck air out of it, you can see we are able to actually capture quite well the surface profiles. And we're talking about only a few millimeters of changes. And then we actually did it on some volunteers. This is actually my ear. And we were indeed able to capture the curvature, as you can see in this through this method. But there's a problem with our ear. You heard the previous speaker also talking about diffuse reflectance. When you have a surface that has some kind of subsurface components where light is able to also go through the surface, bounce off randomly, and then come back, it creates a problem. So I wanted to. This is be the take-home message. If you missed everything else out, this is the central concept of what most of the results that I show. A scene. A normal scene around us always has, almost all the time, has some surfaces that are diffuse. A glass of milk, some, a fruit or a vegetable or things, a lot of things, an egg. The reflections that are coming to our eyes directly from the surface, I would call them as direct. Anything that goes and is bouncing off many times through the surface and then coming back to my eyes, I would call that as a global component. So the computational challenge here is, can I separate out the two? Our eyes can't do that. We're seeing composite images, but computationally the camera could separate it out. And I'll show you some more examples here. If this is some normal eggs, right? You capture a picture. This is the direct component, and you can see that the global component is that halo that's coming from the eggs. More interesting is actually these bell peppers, capsicum. If you look at the direct component, there's nothing. So most of the light that's coming is actually from subsurface. It's not the direct part. So and different objects can actually have a different ratio of the global versus the direct. But here you can see some contrasting examples where for these bell peppers, you don't even see it much. It would be if my eyes were just looking at the direct reflection, I wouldn't even see them. So how would you do the direct global separation? It's actually pretty simple. You can use the same exact method, and if you notice in the I could go back to the slide for where we had the equations. Pretty much this equation, the IN, I can now add the global and a direct intensity components to that, because I'm assuming that most objects that I see around do have this, and the eardrum does have it because it's a translucent object. So if I were to add a direct and a global component, then all I need to do is again solve for the LD and LG here. I know phi's because I am that's what I'm modulating. I can use the same projector, fire a set of patterns. The first step would be to get the to solve for LD or LG, one of them. If I can solve for that, if I solve for the direct, I get the global, and vice versa. And then I can use another set of fringe patterns to calculate the depth. And this time when I calculate the depth, I can subtract the global, or pretty much the global component, because I don't want, I want to capture the surface accurately for doing depth measurements. So that would be pretty much the goal here. So this is an actual eardrum. If I were to look at, and this is where the global direct separation has already been implemented, you can see that the fringes are all separated out on the surface, and the background here is what you can see. That's the global component. So it's very interesting. You can actually now start to see behind the middle ear. It's like I put like a translucent film on my face, where you barely can see my face. But using this technique, if I'm able to subtract out the direct components, I can actually start looking behind the screen, and I'll be able to see my face. And in this case, it's inside the middle ear. So we see better. It's slightly noisy, but the depth contour here you can see has become better now that I'm only looking at the surface to do the 3D reconstruction. Here are some other examples. This would be a normal image versus an image where the direct component is removed. Some of the examples you can see here. If I were to just look at the direct part, you can see it is those images will be high. The sharpness is going to be much higher because the high frequency features are captured in the direct part. The global part is more like, it'll be a blur, but I can see deeper with the global part. Here are some more examples. You can actually see here in the normal image, you can't see these the internal bone, the pattern of these bones, the inside the ear, and you can actually see that in the global image because I'm removing surface reflections using the computation part. We also extended this to looking at other parts in the in the space of the ENT, looking at something like tonsils. It's not difficult to diagnose tonsils, but doctors actually want to know something called a Brodsky classification. They want to know what is the volume of the tonsils, and there are actually 4 grades of that, and when they should operate. And you can only get volume if you're able to capture 3D information. So we kind of modified this, created like a phantom, which kind of mimicked somewhat the cavity near the throat. And here you can see we were able to simulate the 4 scales, 4 Brodsky scales of the tonsil, basically tonsillar hypertrophy, which is the term for enlarged tonsils, and we could actually capture the volumes and the depth information quite accurately. So it could be a useful tool for doctors. So we could go a step further. What if the phase was also had some relationship with time? So you could actually get 3D videos now. Because in the previous case, you were able to get depth, but it was a static image. And there are actually people who have used our work with some more with a high-end GPU and things like that, because of doing a lot of processing, and you need a very fast projector to flash like hundreds of frames per second, but you could actually capture three-dimensional videos in that case. Again, so extra computation with some extra hardware, and probably end with another. Just this is nothing to do with health application, but just for completeness. What if I were able to also capture the angle? So color, intensity, and also the angle. The angle again is related to depth, right? If I were, closer to an object, the angles, basically, if you consider the light to also have what we call a light field, which also captures the angle information, then we could also do some kind of depth imaging. This time, I'm not changing the lighting, but I'm changing the sensor, doing some modification to the sensor, and the image that I get from the sensor will require some computational reconstruction to get back. And I'll show you how. So the top here, that's a normal camera. Just there's a screen. There is some kind of pretty much our retina or the CMOS sensor on your phones, and some kind of a lens. In a light field camera, what can be done is, if you were to have a set of micro lenses sitting on the sensor, each of those lenses will now start refocusing the light, being very sensitive to the angles that it came to, that the light was incident to. So in this system, then what I'll have is multiple images being captured simultaneously on a sensor, which have the coded information of the angles. So what you would see on your camera is the raw format would be like like an array of images, each of them having different angles. Now the computational challenge is, how do I create a composite image that has a one-to-one correlation with the scene that we are seeing? And if you were able to do that, and people have done that, there's a very interesting thing that comes out from this. So let me play this just before I finish. What you will be able to do is this. You can take an image like this guy blowing out candles. Once you capture it using the light field camera, you can refocus after you've captured the image, which is amazing. Like, you pretty much do not have to, take the camera, try to focus. It takes some time. We're trying to do some kind of photography. Sometimes things are out of focus. Sometimes a really nice memory that you were trying to capture is out of focus. You could use this kind of a camera, capture an image, doesn't matter. Just get the frame correctly and refocus. Like, if you don't want somebody, you don't like somebody and they're in the background, sometimes the photo bomb or whatever, you could just blur them out later. And this is not the same as doing a digital blur. This is actually the information that's captured in the image. So the image file is very large because of the type of the format. But the benefit is you can do post capture focusing and things like that. So let me summarize. So we talked about pretty much, we started with the scene. The scene has, you're trying to capture a scene. There is an object they're trying to capture. There is a sensor, there is some kind of optics, there is a lighting, and there is some computation, post-processing. And we looked at things that we could control in a computational manner. We looked at the examples from my research that looked at phase modulation by using a projector as a medium to create the modulations. That could capture depth. We could also go a step further and separate out direct reflections from subsurface using the similar method. And we could then also start looking at phase as a function of time. You could also look at the time differences to get depth. So taking the same image format and then trying to control a lot of things around it with optics plus some kind of computation. That would kind of sum up what what I'm trying to convey. So yeah, all right, thank you. I hope I was under the time limit, and yeah, I'd love to answer any questions.
Thank you, sir. We could now have some questions. Bal Mukund brother has asked.
Oh, yeah. Please see.
Yes. Manoj brother has asked how Microsoft Kinect is different from PDAF sensors used to mobile cameras.
Oh yeah. The Kinect is very different. Each pixel on the Kinect sensor actually has its own light source that is modulating it. So you can imagine like there are infrared light sources on each pixel. It's sending a light beam and it's waiting for the return phase to be picked up. So all the cameras that we use normally in our phones, etc., they only have pixels that can detect light and color. That's it. In the Kinect, we're looking at each pixel being able to detect depth. So the hardware itself is capable of detecting the depth. We are not doing some kind of processing or anything to kind of get the depth.
One more question, sir.
Yeah, go ahead. Is it here or?
No, sir.
Any other questions from the audience?
I can hear, yes. Okay. Can an otoscope damage our ear? The only way it will damage it is there is a specula which guides the light inside. If that touches the eardrum, it can hurt or damage. But the design of the specula, it's kind of tapered, so you can't actually push it all the way through. But anyone untrained can cause damage. So, but there is no light damage. Like the light that we use are just either LEDs or a projector. So the light will not be harmful. But yeah, physically, don't try it on yourself. How much data are we looking at when we process them? Oh yeah. So in computation, images you're taking a lot of images many times. You're taking maybe, like for the light field photography example, one image can be 500 MB to 1 GB. Then there are other challenges on how you can work to compress them and things like that. Many times they use a GPU to capture. You need, like, if you're trying to do something real time, you need fast processing. So that is definitely one drawback of using a lot of computation.
One more question. What is the kind of topographical resolution or depth you can get currently with your system? When you do this mapping.
Yes. We were able to go down to about a millimeter or half a millimeter to 1 millimeter. Yeah, so it's not like it wouldn't be considered like a high resolution. It won't be like an OCT or some of the other techniques, but there is always the dynamic range part. Like I can go from a few millimeters to a few centimeters with the depth, the field of view that I have. Whereas the Kinect could go for the Kinect, the resolution is a little worse. It's probably few millimeters. So yeah, so there's always this balance between the dynamic range and the resolution.
Okay. There's one more question in the chat by Abhishek.
When you talked about focus change in the images, you have a raw image which will be digitally focused. No, this is not digital focusing, right? That's the difference. When you're trying to do some kind of digital focusing, you would either put some kind of filters to increase the sharpness of the image, or some kind of thresholding, etc. But this is you can imagine this, the image that is captured in a light field has all the different focal planes squished. All the information is squished into one image. So the closest example I can give you is like focal stacking that you would see many photographers use. It's like you change the focus, take an image, change the focus, take an image. So if you were to combine all of those images into one, overlay them, that would be the closest analogy for what is done. So it's not a digital refocusing. In high-speed imaging, do we compromise on resolution and magnification? Yes, quite a lot, I think. Yeah, because as I said, for example, if you're looking at each pixel to have more features, like in Kinect, right? Kinect has a very low resolution. It wasn't designed to do high resolution imaging, because now you're not only putting like silicon photodetectors, an array of that, you're also putting other things like its own light source, some kind of a receiver, along with the usual color sensor. So you cannot compress all of that into like megapixel resolution. So there's always a trade-off when you're trying to do fast. Like the streak camera, the resolution is really poor. And then Tanu's saying, in the last slides, you mentioned that we could do some manipulation in our data captured. Then where do we draw the line in actually looking at reality? Yeah, super, very good question. Because we are applying a lot of computation, and so there, it's likely, if we are not careful, there's very much likely that this can happen. So the best ways are to have robust calibration. Like for example, before I start doing the ear imaging, I would take slides that have very well defined thicknesses. These are used in calibration of ultrasound equipment, etc. I would take those, I would measure those with my device before I actually start looking at more complex objects. So the calibration part needs to be done very, very carefully. Then I also need to know exactly my optical configuration, because many times I'm looking at indirect depth information like the phase, and I need to convert that into dimensional units like centimeters, millimeters. So yeah, so we do have phantoms that we use. We do have calibration, the slides, etc. All of that needs to be done. Yeah.
Sairam, on behalf of the department, we would like to thank you for your insightful talk and spending your valuable time with us, for sharing your knowledge.
All right, thank you so much. Yeah, feel free to reach out if anyone has more questions offline.
Yes.
All right, thank you very much.
Thank you, sir. Due to lack of time, we'll not be having the break, and I request the next speaker to be introduced.
Om Shri Sairam. My most humble and reverential pranams at Bhagwan's divine lotus feet. Good morning, everyone. Now I have the pleasant duty to introduce our next speaker for the day, Dr. Shashwati Sen. Dr. Shashwati Sen completed her MSc from Devi Ahilya Vishwavidyalaya, Indore, and joined the Technical Physics Division of Bhabha Atomic Research Center in the year 1997 through 40th batch of BARC training school. In the initial years of her career, she worked on high-temperature superconductors and completed her PhD on the same topic from Mumbai University. Later, she started working on various nanomaterials like tellurium, tin oxide, tungsten oxide with application as gas sensors. Currently, Madam is heading the Crystal Technology section of Technical Physics Division BARC and is working on growth of single crystals and transparent ceramics for application in radiation detection. Further, Madam is collaborating with the Department of Physics at our institutes for 3 years on the Gamma Camera project. Dr. Shashwati Sen has received many awards, which include the DAE Science and Technology Excellence Award in 2017, the DAE Solid State Physics Symposium Young Achievers Award in 2008. She has also received the DAE Group Achievement Award in 2008 for the work on gas sensors and in 2014 for the work on growth of single crystals of cesium iodide and sodium iodide for radiation detection. In addition, Dr. Sen has over 200 publications in various international peer-reviewed journals and more than 3,500 citations to her credit. Dr. Sen will be addressing us today on the topic Scintillators in Healthcare. I now welcome you, Madam, to deliver your talk.
Good morning, everyone. Hope you are able to listen me. Thank you for introduction.
Yes, ma'am.
Thank you for the introduction. And, let me first thank the organizer for giving me this opportunity to be part of this meeting on healthcare. And many thanks to Professor Shiv Shankara Sai for collaborating with me and making me a part of the family for SSIL, for the Satya Sai Institute of Higher Learning. And okay, so my presentation, is the presentation visible?
Yes, it's visible.
It's visible. No, okay. So I am a material scientist, so not exactly imaging kind of work, but I'm working on materials which are used for medical imaging. So these are the scintillator materials which are used for healthcare. So, so I will start my presentation with what are scintillation. So scintillation is the process in which a high energy photon, like a gamma ray or X-ray, can be visualized. So when a gamma ray or a X-ray falls on a scintillator material, which is generally a single crystal, it causes ionization inside the material, and this ionization leads the conversion of the high energy gamma ray or the X-ray to a low energy photon, which is a visible light photon. And this light photon can in the next process can be we can detect it using a photodiode. So which can be a photodetector, it can be a photodiode, or it can be a PM tube or any other like a CCD camera, and which gives rise to the electronic pulse. So this is the scintillation process. So why it is required, like my previous speaker was saying, like we require things where what I cannot see, we have to see those things. And more so when like radiations, high energy radiations, gamma rays or X-rays are there. So they need to be detected because for both the reasons, because they are harmful and also because they are useful also. The humankind and the science has come to the phase where we have put this harmful or high energy radiation to useful applications like medical imaging. So for imaging purpose, you have to detect, and to detect you have to make them into a electronic pulse or an electrical pulse, because all our machines or instruments are based on electronics or a electrical pulse or a electron, basically a pulse of electron. So this photon, how to convert this high energy photon to a electronic pulse is by converting the high energy gamma, high energy or high frequency electromagnetic wave to a low energy electromagnetic wave, which can be then converted. So the ionization radiations which I will be talking here is mainly gamma and X-ray, but gamma and X-ray, because they are what we are using in healthcare. But these scintillators can be used to detect synchrotron radiation also, alpha, beta, electron, proton, and neutrons. So scintillators are basically all those. So here it is the electromagnetic spectrum, and these are the regime where I will be talking about. So we have got hard X-rays and gamma rays. And medical imaging techniques which are using these high energy radiations are radiography, computed tomography, that is the CT scanning, and then nuclear imaging processes like PET, which is the positron emission tomography, and SPECT. SPECT is the single photon emission computerized tomography. So these are two different categories. Radiography is the normal X-ray plate which we are doing from childhood. We know when there is a fracture or something, we go to the doctor takes an X-ray, and that is the radiography. And computed tomography, CT nowadays, and because of COVID also, we keep on hearing that doctor has done a CT scan. So what is CT scan? CT scan is also a radiography, but it is like you are taking the radiography or the X-ray scan of the body or any organ of the body at different angles. And then these many radiographs are then using computer and imaging techniques. They are put together to make a 3D. So basically these two techniques are anatomical images. But nowadays, because of nuclear imaging processes and radiopharmaceuticals which are used, we can do functional imaging also, like how the blood is flowing or how there is a tumor in the body, you can find out, or like heart pumping and all those things. So in this case, nuclear image, a radionuclide, radioisotope is injected in the body, and then they are detected. So in PET, for positron emission tomography, a positron emitting nuclide, generally sodium 11, is injected into the body, and it is a positron emitter, and this positron then gets reacts or interacts with an electron in the body, and then it gives rise to two photons which are emitted at 180 degree in different directions, and then these photons, which are of 511 keV energy, they are detected. So that is the, and by this you can find out the very exact location of tumors generally. And SPECT is the single photon emission computerized tomography. It also uses a gamma emitting, but here it was only a positron emitting, but here we have a gamma emitting radionuclide, which takes a two-dimensional picture. And then this is gathered on a scintillating camera, and then planar images, many, and then there is a reconstruction of a 3D image. So that is a SPECT. So here we can do functional imaging. And so what are the energies? Because when I am talking about a scintillator material or imaging this using materials, we have to know at what energies this the gamma or the X-ray is coming. So for a general X-ray imaging of a radiography, chest radiography or X-ray CT scan, it is 150 kilovolts. But when we are going to nuclear medicines, like in PET, I said it is 511 keV, because that is the energy of a gamma which is ejected in both the direction when an electron and a positron combine with each other. And in case of a SPECT or a scintigraphy, it is in this region, so 60 to 511. So what are the what should be the characteristic of the material of the scintillator which can be used for this. So first thing is like high light output, means the X-ray conversion efficiency, means whenever a gamma photon or a X-ray photon is coming and interacting with the scintillator, it should give out a burst of photons at the lower energy. So there should be high light output, then only, because when you are application, like in case of a medical application, we have to also think of the dose which our of this techniques are giving to the human body. So the material, if to lower the doses, the material should be that it should whatever, if one gamma is coming out, like just a one gamma photon, if it can detect from the human body and give out an image, that will the best, because it will be giving a very low dose. So that is one thing. Next is the high X-ray stopping power. Stopping power is means when a high energy gamma is coming and interacting with the scintillator material, the scintillator material should be able to stop it. The stopping is required to produce a proper image, because if it passes through it, if the material is transparent, then it is not losing its energy in the scintillator material, then obviously you will not be able to get the maximum output. So you need a high X-ray stopping power. Then good spectral match with the photodetector. So whatever you are using a PM tube, or you are using a photodiode or a CCD. So the output, the emission wavelength of the scintillator material should be matching with the photodetector. Then there should be decay time should be very short, because like in maybe not so much important in case of a radiography, but when you are doing a medical nuclear imaging kind of technique, where you are doing imaging of some functional organ of the body, you should be able to detect the next step. So the first step which has given out some images, or the photon burst which is have been created from the first step of your organ in the scintillator material, it should die out so that the next step can be. Otherwise, we will be seeing the ghost images. So basically, this short primary decay will lead to low afterglow, because that ghost images is gone. And then radiation damage resistant, because it should be like long, it should be stable, it should be hard, and it should not go bad very easily. Then with time and temperature, because you are working, can go to very remote places also, compact and easy packaging and all those things are there. So what are the materials which are used for this? So this I will not go into big jargons and all those things, but like in my earlier slide I was saying about, so how those key points are coming into material characteristic. So when I am saying stopping power, good stopping power, so it should be having high density. So here you can see whatever scintillator materials we are using has to be used in this, like this is gadolinium oxysulfide, cesium iodide, thallium, which I will be talking. Then cadmium tungstate, zinc tungstate, calcium tungstate, BGO, which is one of the machines used in PETs. Then lutetium aluminium oxide, lutetium with different dopants, luap, lutetium silicate, and then sodium iodide. So you can see, except sodium iodide, these are all very high density materials. So whenever a gamma photon of say 511 keV is coming, so even a millimeter or a centimeter thickness of this material will be able to stop it. Then very high light yield I was saying. So this is the photons per MeV. So like 1 MeV of incoming radiation will lead to a photon burst of 40,000 photons at a lower wavelength. So this 40,000 of our cesium iodide, it is like 61,000. So when I am talking about 500 keV of energy of an incoming photon, so half of this, so like 30,000 photons I am getting whenever one photon from a positron emission tomography is coming. So this kind of materials are very useful. Then here it is the decay time which I am talking about. So you can see for a cesium iodide, it is 900 nanoseconds. So that is around in microseconds. But this is fine when we are doing radiography. But when we are going into nuclear spect and PET kind of thing, we have to go to very fast, because we are imaging the functionalities of the human body. So 40 nanosecond, 30 nanosecond, or even faster materials are used. And here it is the emission wavelength. So you can see this is around 500 nanometer, which is the green light of and most of the PM tubes or the silicon photodiodes has got very good matching with these wavelengths. And this is a 1/T. So I will not go into. So we can see from the earlier chart also that no material can have all the desirable properties. So we are working on more than one material. So here I am just giving a very no, a fancy photograph, you can say, of the different scintillator materials, except germanium obviously, which are used. We have, our group has been working in BRC. So these are all single crystals. Single crystals are mainly required in scintillators in applications, because one thing is that single crystals are transparent to their own luminescence. Means whatever luminescence is forming, whatever photons are getting are generating inside, they are luminescent. It will be, they are transparent, so they will come out and you can use any photo detector to detect them. And this is gadolinium gallium garnet, one of the new materials which are coming up for in use in a SPECT or PET kind of machine. And this is YAP, yttrium aluminium perovskite. This is sodium iodide thallium, which is one of the oldest material, scintillator material available. And this material is used in different forms in radiography. So whatever radiography plate we are using a thin film of sodium iodide thallium base. So that I will be coming to later on. And this is the lutetium silicate, which is used in SPECT machines nowadays. So these are there. So how does X-ray radiography looks like? So basically, when you are going to the chest X-ray, say, so this X-ray, medical X-rays are there. So it is coming, and you have got a camera here, which is recording the. I'm talking about the digital. Earlier, there used to be this sodium iodide, sorry, this silver iodide screen used to be there, and which has to be developed, and you see. But nowadays, when you are going into digital radiography, so there is this scintillator screen is there, then this is the sensor, photo sensor, and then there is a camera. So the scintillator will see, so whatever X-ray which has passed through the body, so depending on that you will get the contrast in the image, and that will be detected here. So in to decrease the cost of these things, because in India these whatever scintillator screens and these machines are not yet being made. So our group has started working on indigenous development. So there have been, we have used two techniques to make the cesium iodide thallium crystal. So one is a mosaic of this crystal, and other is a thin film. So I will be talking about that. So we are putting this mosaic. So this is around 200 mm, means 20 centimeter by 25 centimeter. Long plate is there. And then we have put a normal CCD camera, which is our DSLR camera. So how we can use that? So first is like one is like cesium iodide thin films, which we are working on. So thin films, any material scientist or PhD student will be know, like whoever is working on thin films is this is a thermal evaporation system. Very easy to use and very economical, and most of the lab has this. So we are putting our cesium iodide on this resistively heated filament, and putting our substrate, which is generally quartz plates, on this, and evaporating the cesium iodide, and we get this kind of films. So this is the microstructure of the cesium iodide film. The cesium iodide has got this very good property that whenever a film is growing, sorry, it is a micro columnar kind of structure, means this is needle shaped structures are there. And as you see, this diameter of one needle is say 10 micron micrometer to 20 micrometer, and not more than that, and very regular. So this basically this needle shaped structure is a single crystal in itself. So whenever a photon is coming, a high energy photon, a gamma photon, or X-ray, like we are doing X-ray, so it is coming and impinging here, is it being absorbed. So whatever the burst of photon it gives up, it is getting collimated. It stays within this one needle, and so there is and then it travels and get detected with the photo detector. So if it is a specially resolved photo detector we are keeping on top of this film, so whatever information photon which is coming and impinging on this part is coming from this. So there is a lateral one-to-one correspondence because of this needle like structure, so that this photon which is coming, burst which has been produced, it will not go to any other direction, it will be collimated in this. So this leads to a very good resolution, spatial resolutions, otherwise there will be crossed out. So this is one way. So these are the few I am showing for photographs of the cesium iodide, and this is 200 micron thick cesium iodide film on silica quartz substrates which I've done. And after deposition we have to do the luminescence studies, and this is the line pair resolution. Line pair resolution is like which is the minimum resolution lines are there which it can differentiate. So we have been able to achieve around 50 micron line pair resolution. So any defects, like if you even have a fracture in your body and any bone, which hairline fracture like 50 micron or something, hairline fracture, your hair diameter is 100 micron. So those kind of fractures we can detect using our films. So this is again, and here just for testing, this is the printed circuit board of a multimeter which you can see, and this is, so image is different. So resolution is 5 line pair per micron. Here is the, so this kind of structure we are making. So this is one material, and our group is working on this. And next is like mosaic structure. So when you have to do very big screens, and mainly this is not much for healthcare, but when industrial application is there to image, like NDT imaging is required to find out if some corrosion is there in a very big pipeline, or some turbine, there is a crack in the turbine. So here it is not very easy to deposit very large and very uniform thin films. So here what we have done, we have cut the crystals, which I will be coming later on, and then we have make a mosaic. So this is like 3x3 mosaic of say cesium iodide crystal, and normal, then it has been mounted, and normal DSLR camera we have used. So this is the remote of AC remote is there, so you can see all the printed circuits inside, how it is there, and this is the line pair resolution. And this is multimeter normal, so PCB tracks are there, and this is a human palm phantom which I've taken. So we can see a lot of detailing, so can be used. So that X-ray is shine, then you are putting the object, and this is the photograph. Now I'm coming to the CT scanner. So how does a CT scanner is different from X-ray? Basically, CT scanner is like your patient is there, and you have this X-ray source, and this X-ray source is rotating around the patient, and you have full 360 degree of detectors. So this is a ring of detectors, and these are segmented detectors, so which is all around it. And whatever images are there now, this you are getting a 360 degree image of the patient, and then it is these images are all stitched together by computational method, and you get a tomographic. So here, as you see that these are segmented detectors are there. So these are also cesium iodide, which even commercial CT scanners are using is cesium added. So here how we have our work has started working on this. So this is a normal cesium added crystal which we are growing in our lab. So cesium added single crystal is grown by a method called the Bridgman single crystal growth technique. So here we melt the cesium added material, polycrystalline material, and then very slowly cool it. And this is a 50 mm diameter and 100 mm around 50 mm length crystal is there. So from this crystal we have to now take out a part. So these is a square part which we have taken out. So, and this you can see, this is the glowing. So this is how the scintillator process is. Under normal light, this is how cesium added crystal looks like. But when we are putting it under UV in this case or an X-ray, it gives out radiation photon at 550 nanometer, which is this yellowish kind of thing. So we are making this crystal plates. And for that plate we have used for the earlier, I have shown that mosaics crystal. But when we are making a segmented detector, so we have to either have a 2D matrix or a 1D matrix. So the crystal which we have grown, this is a cesium added. First it has to be cut, so we make it into cylinders, and then we slice it in one direction, then we rotate it and slice it in another direction. Also, to prevent any crosstalk from one pixel to the another pixel, we have to put reflectors, and then for full packaging. So in this way we have done. So like the single crystal was segmented, then optical cement by making a TiO2 resin and hardeners were made, and then pasted on all slides slices of cesium added crystal. Then in this way we have made a 1/8 pixel size of cesium added, and then 8/8 pixel. So you can see. So this was the crystal. Initially you have seen how the crystal looked like. Then it was cut into a cylindrical pieces, and now you can see this is a one-dimensional matrix and this is a 2D matrix. Means hereby 8 cesium added pixels, 8/8 are there. So this is a 2D matrix is there, and this is 1D. So there are in this photograph you can see there are 16 pixels which are there. So these are used when we have to do the imaging. So this 16 pixels I have shown. So these are the 16, and this is the radiography image of this, like to show that how uniformly they are stacked together. So each pixel of the cesium added is the width is 1.4 mm, the thickness is 3.2. So sorry, this length is 3.2 mm, this is 1.4, and this separation between these two is 100 micron. And this separation is very important because that is how it has to be matched with the your photodiode. And this is required because if you want to do any medical imaging, you have to have very good spatial resolution, then only you can detect. And I think that is very important for doctors to know exactly where any ailment is located in the human body. And this is the photograph of the photodiode on which these are mounted. So they are mounted on this using some optical glues and all. And this is how they look after, and then we have to do the full packaging. So this is for 1D array. But there are, I have shown the 2D array also, 8/8 matrix. And this 8/8 matrix of cesium iodide on position sensitive PM tubes we have mounted. So this work we have done on our lab also, and we are also doing this work with the Satya Sai Institute of Higher Learning in collaboration with them for use of a gamma camera, which can be used as for detection of lymphatic nodes in patients. So basically this will be a very small, this position sensitive PM tube. It has got 64, means 8 by 8 matrix of photomultiplier tubes, which are inside this. This is a commercial product, but this size is like just 5 centimeter by 5 centimeter. And we have mounted our cesium iodide pixel on this and made this kind of small device. So you can see this is our laptop and this is the device, whole device, and it has got some all readout electronics, including the readout electronics. This is such a small device. This device, you can see, this is the scintillator is mounted here, then this is this device, and on the back there is the readout electronics, and directly it is connected by USB to the laptop. So this small instrument is very useful when we want to detect any, it can be used as a handheld gamma camera, which is the work which we are doing with the Satya Sai Institute of Higher Learning. And at our lab, we have tested this device. So this is like there is 1, 2, and 3 radiation sources. So we can see the radiation sources using this. And now we can also move it because it is a very small and can be packaged properly. So these 3 sources we have detected. So if like any radioactive medicine is injected to a patient, like for iodine is injected for thyroid glands. So if it goes and gets absorbed on the thyroid glands, basically these whatever is injected, they have like glucose based medicines are there. So whenever there is any tumor coming up in any organ, basically thyroids and all, so these tumors has got the they have got this, they try to absorb glucose more and more. So these radioactive medicines also go and start setting, and we can very well find out their position. So if you see this within a 5 centimeter by 5 centimeter, we can find out very precisely using this device with the position sensitive PM tube and our matrix of cesium iodide, how it can be used in medicine. So this was a lab source which we have done, and now with actual human phantom we will be doing at this institute, Success Institute. And now for a PET scanner. So as I told you, this positron emitting radionuclide is injected. So it emits the positron, and then it interacts with an electron, and it gives out 2 gamma photons of 511 keV each. So like if it is coming here, it is, and so we can exactly find out the position of this tumor, and it can also see the functioning of this in this case. So this is the PET machine. That is how it works, like in the head, in the brain, or in the chest or something. So the scintillator material in this case is not, we cannot use cesium iodide in this case. One thing is that cesium iodide has got afterglow. So because for PET, we have to do detection of 2 gamma photons we have to do. Because when we are detecting 2 gamma photons simultaneously, the precise location and working can be found out. So cesium iodide is a slow scintillator material, so it cannot be used. So we have to find a better high fast scintillator material. So main requirement for a PET machine is mainly is timing resolution, and then other is like high light output, fast decay is the timing resolution, high density, high atomic number, all those are remains the same. Good energy resolution because you have to detect this 511 keV among other things, and non-hygroscopic and other things. And then advance of this PET is time of flight PET is there, and other things. And in case of spec we are doing, we had some radioisotope, gamma emitting radioisotope is there. So it should have lighted, good lighted, and resolution. Time, spatial resolution as well as temporal resolution. So spatial resolution is done by using collimators, where the PM tubes, like PM tubes are there. So we have to put collimators before that to maintain the spatial resolution and temporal resolution, because it has to be very fast. So some of the materials which are used for this PET and SPECT is like lutetium silicate and gadolinium gallium garnet and lutetium aluminum garnet. These are things. So lutetium silicate and gadolinium gallium garnet our group is working on. So I will be showing some results on that. So lutetium silicate is a material which melting point is 100 degrees centigrade. So to make this for the SPECT and PET, you have to use single crystals. You cannot use 10 films for that, because these are high energy gamma rays, gamma photons which are coming. So you need a single crystal to absorb them. Also, you need the energy resolution. So when energy resolution is required to be detected, so we have to use a single crystal in that case. So the growth temperature is 2100 degrees centigrade. So it is very difficult to grow this material. So, and the second material which I was talking about is gadolinium gallium garnet. So its a melting point is 1850 degree. So these materials are grown in a Spectroscopy technique, which I will come in later. So this is a Spectroscopy crystal growth technique. Here the material is kept in a crucible and then it is melted. The melting is at a very high temperature, as I said. And this crucible, normal any material cannot be used. So you have to use very high melting point metals. So metals and which are not interacting, which are not reacting with the melt. So this is either iridium crucible or sometimes people are using molybdenum or tungsten, like that. And then the crucible, the crystal seed is come and it touches the melt, and very precisely using rotation and translation, this is pulled upwards. So this is called the seed rod. The seed of the seed crystal comes and touches the melt, and then it is pulled upward, so that there is a first the nucleation site is there at the seed, and then very slowly the crystal keeps on growing. So this is how this crystal, you see here the photograph. So here we have grown. So this is the gadolinium gallium garnet crystal is there. So, and this is around 30 centimeter diameter, 30 mm diameter, 3 centimeter diameter, and around 5 centimeter in length. So this one crystal growth takes place in say 1 week. So crystal growth is a very slow process, and you require a lot of patience. So this is how we have grown. So so these are now we have started working on their applications in healthcare. We have already tested these materials for their use in radiation detection in our Department of Atomic Energy. Various users are using them for safety purpose or detection of gamma rays. And now we have taken up this challenge of using them for indigenous development of PET machines. Now, when I'm talking about healthcare and radiation detection and healthcare, so radiation, these in the earlier materials which I was talking about, we are detecting the radiation in situ, means live detection of radiation is there. But there are materials which are called radiation dosimeters. So these materials are required to store, they store the information about radiation exposure, and then this information can be retrieved either in situ or ex situ. So why we require these kind of materials? Because one is the radiation worker, like in case of reactors also, but in medical healthcare, a person who is operating the radiography machine is exposed to a radiation, X-ray radiation, or even a patient who undergoes a kind of treatment, so they are exposed to radiation. So how much radiation one is getting exposed to, we have to account for those, and whether it is permissible or not. So in general, as per international norms, per year a human body can have a dose of 20 millisievert. So natural background is there. So here you can see when you are undergoing one CT for abdominal region, you are exposed to effective radiation doses 10 millisievert, which is comparable to natural background radiation of 3 years. So 3 years you get, so this much radiation you are getting. But and then when you are doing normal bone X-ray, that is 1.5 millisievert, and this is 6 months, so 2 millisievert when head CT is there. So these are the differently comparable, and international standards say human body can be exposed to 20 millisievert per year. So that is a permissible limit. So we should be aware of this, and a technician or a doctor who is working with these medicines, so we should find out, it is required to find out how much they are getting exposed to. So these dosimeter materials are required. So we have been working for this. So this is the how this is the radiation. So one is air exposure, which is the amount of ionization which is caused in the air by the gamma ray. So that is called the. But when a material absorbs these doses, so it is recorded in gray. This is the gray amount of radiation energy absorbed in material. But when it absorbed in equivalent dose, it is resulting this absorbed dose, equivalent dose in human body. So it is measured in sieverts. So this material is one of the very good dosimetric material which our group has worked on. This is the lithium tetraborate. Lithium borate crystals are there. This is also grown by the Spectroscopy technique, but its melting point is quite less. It is around 900 degrees centigrade. So not very difficult to grow, but there are difficulties in this growth because this grows at a very small speed, and we have to do a lot of material engineering to get good dosimetric output. So these are the photographs of the lithium tetraborate crystal which I've done. So this crystal has got is that it can detect very low doses, and then it can be used for both neutron and gamma exposure. So gamma exposure is the main for in the healthcare, but for in our kind of work where we are working in reactors also, so neutron is also required. I'm sorry for this. And then can be used for both personal and medical dosimetry. So personal is like I was talking about healthcare workers who require, but medical dosimetry is like when you are giving some doses to a patient for cancer therapy or something. So you have to find out exactly how much dose we are giving. So when you are exposing a tumor to a cobalt-60 radiation, so like 1 gray is generally given at a time. So whether precisely measurement of this 1 gray dose has to be there, and how much the surrounding tissue is getting exposed, these are the some things which is required to know in radiation therapy. And how this dosimeters work is that they absorb the radiation, and when this radiation is falling on them, they create some kind of trap centers are there. So this the electrons which are created by this radiation gets trapped in the trap centers, and when either we are then stimulating this material by thermal heating or by optical stimulation. So this is when we are using thermal heating to read out the dose information. It is called thermally stimulated luminescence or optically stimulated luminescence. So these are the two techniques on this these dosimeters are working on. This is TOSL, thermal stimulation, that is thermoluminescence, and optically stimulated luminescence. So thermoluminescence, but small chips of these crystals, very small chips are used for dosimeter. So we are putting it on a temperature control heater, and we have a photomultiplier tube which will be recording the luminescence which is coming from it, and this heating and is started. and we get this kind of a curve. So this is like the glow curve, we call it the glow curve, TL glow curve. And this we have measuring the intensity, and this is the temperature. And this area under the curve gives the amount of dose which has this chip has seen, this crystal chip has seen. So like I'm writing at 3 microgray. So this was the minimum dose we were able to measure using this this crystal lithium tetraborate. And this is the linearity of this. So you can see in microgray to 1 gray, even more than that, it has got linear behavior. And this material we have used for medical dosimetry. And for medical dosimetry, when we are using it for it has been used in human phantoms. So we require very high reproducibility, so that the variation from one chip to another, one crystal piece to the another crystal piece, should be less than 2%. Because whenever there is a repeated radiation or a radiation at different position, it has to give the same values. So we have did 120 different samples where find out.
Sairam to everyone. Dr. Shashwati Singh got disconnected, so we'll wait for her to connect back.
Hello. Hello.
Yes, ma'am. Yes, ma'am.
I'm extremely sorry. There is some network problem from my side. Okay. I will resume my topic. You can see that. So I have you have been here, no?
Yes, yes.
Yeah. So I will start from the next slide. So this is fine.
Ma'am, can you make it full screen?
Yeah, that's fine. Okay.
Yes.
Okay. So this is the range of we have used our OSL the TL meters. So here you can see we have detected this in microgray and even up to hundreds of gray also. So it can be used in both accidental or personal also. So this lithium tetraborate crystals we have used, we have done some not exactly clinical trials, but field trials for medical dosimetry application. So for medical dosimetry, this is like I was saying for cancer therapy. So when cobalt-60 radiation is given to at different tissues in the body, so exactly how much this radiation is given, we have to measure them. So this you can see human phantom is there. So this crystals are put at different places and then it is measured. So we have taken high quality 120 samples we have taken with the variation is less than 2% variation is there. And these were used for verification of dose during radiation therapy at Linac-based radiation therapy center at Atonic. This is a DAE center at Navi Mumbai, Kharghar. So here you can see centigrade, 214 centigrade, and these are the different doses which was given. And this is our measured by our crystals. So you can see very good matching is there. So now the phantom trials are already over and we are looking forward for the actual clinical trials where they can be used in patients. So we have done this kind of work also and going on. And optically stimulated luminescence I was talking, where we are stimulating this radiation dosimeter by like a green LED or a blue LED. And then this kind of decay curve, because they are getting de-excited from their tap centers, so we get this kind of decay curve. And this area under the curve, if you plot, that is the actual dose. So this optically stimulated luminescence, because we are reading the dose, we are retrieving the information about the dose by just using a LED. It can be used for in situ detection of radiation when you are giving it directly to a patient. So like, because the crystals are very hard material and this is lithium and boron is there, so it can be used in a catheter and directly put inside the patient at the exact site of the tumor, wherever the tumor is there. And then when the radiation is given, so the light output from this, it can be this luminescence signal can be taken out using a fiber optics, and we can directly read. So this is one potential application of this crystal for radiation therapy, like in situ detection of actual measurement of the radiation doses. So these are various work which our group has been doing on the healthcare area of with radiations. And this is our team at Crystal Technology Lab of BARC. And thank you. So please let me know if you have been able to understand the work or if you have got any questions. Please let me know. Thank you.
Thank you so much, ma'am. Any questions from the audience?
Yes. Thank you, ma'am. Thank you for such a wonderful, insightful talk. Students definitely benefited from this, very educative talk. We're also happy to know that BARC is doing such a wonderful work of developing sensor crystals for varied applications. Very happy to know that. And also happy to collaborate with such a premier institution and such good work you're all doing. My question is...
So the pleasure is totally mine to collaborate with your department.
Yeah, it's mutual. Thank you, ma'am. My question is, now, since this technology is now well developed by the BARC, any Indian industries have come and then taken this for translation into devices? Well, we hear only Saint Gobain and such big, MNCs to be making.
No, sir. I think very actually, sir, we have given the crystal growth technology for cesium iodide to two person. One is ECIL Hyderabad, very near to you. So though ECIL is a part of DAE, but it is a commercial organization. So we are R&D people. So we cannot cater to the requirements of the general public.
Correct.
But ECIL, we ourselves has gone to ECIL. We have set up the crystal growth labs. And cesium iodide, sir, they have started working on it. And now they are growing the crystals on their own. So very soon. Yes, sir. Okay. And sir, other is a private company in Mumbai only. It is called And Ceramic. So they have also taken up the this technology for single crystal growth of cesium iodide as of now. And but they have still not started it properly, I would say. So we are still in the process of knowledge transfer. The technology we have given them, but for setting up, because initial know-how transfer and proper hand-holding. So that incubation period is going on. And we are open for any other also if they want to come up, because cesium iodide is one which is used everywhere material. It is easy to grow, easy to handle, and it has got very wide application, not just healthcare, which I have pointed out, like from X-ray baggage scanner, which is extensively used nowadays. So
in airports and then
everywhere, even malls and cinema theaters are using nowadays. So that is one application.
You're also doing the PET also, so you said that deposit on emission tomography.
Yes, sir.
That also has been transferred, knowledge transfer has taken place?
No, sir, no. For medical imaging, sir, there has been no knowledge transfer, because we are also in the R&D stage at present.
Okay. Thank you. Thank you, ma'am.
Welcome.
Ma'am, I have a question, ma'am.
A very slow speed we have to cut, and then when we are we have to also be very precise with the dimension, like I have showed you 1.4 mm, 3.2 mm, like this kind of thing. So there are machines which are available in Indian market. Also there are machines in Chennai based are their companies who can do this kind of very slow speed and very precise cutting. So crystal cutting machines are available, which for the cutting we have to do, and then we have to again put them back together in precise arrays. So that is a different know-how.
Okay, thank you, ma'am. Ma'am, another question we have, ma'am.
Yes.
Ma'am, what gamma emitting radioisotopes are used for the SPECT camera? You mentioned the use of some gamma emitting radioisotopes.
Yeah, actually they are fluorides which are using some fluorine 17 isotope is there. Okay. So which is used.
Okay. Thank you, ma'am.
Ma'am, one more question.
This question is from materials perspective.
Yes.
We have been seeing yttrium-based garnet to be the most popular material for as a single crystal material. your switch over from yttrium-based garnet to gadolinium gallium garnet, from materials perspective, how cost effective it is, because yttrium is more abundant, melting point is high, whether yttrium garnet. So do you have, or have you done any comparison based garnet versus gadolinium based garnet in your application?
Yes, actually, yttrium-based garnet, the most famous yttrium-based garnet is YAG. But YAG is not a scintillator material. YAG is a laser material. So a difference between a scintillator material and a laser material is laser has got this metastable state. That is why you can create this population inversion. Whereas in a scintillator, the decay has to be very fast. So whenever there is an exciting gamma coming on, it should decay fast. So YAG itself is not used, but another YAG based yttrium aluminum garnet is not used. Yttrium aluminum perovskite. There is one another allotrope of this material, you can say, which is used in scintillator material. And in one of my slides, I have shown, let me go back there. I have shown about this lutetium yttrium, LUYAP is there. So basically, when we are using it for say SPECT kind of application, I said one important thing is that it has to be fast. So yttrium aluminum perovskite is a fast scintillator, but there are other scintillators like here I have. So these are lutetium based materials are there, or are more appropriate here. Or if I even go in earlier slides, I have shown where the various materials which are used. Are you able to see the slides?
Yeah, we are able to see the slide.
Okay.
Yeah, I saw in your table, in the first table that you had shown.
Yes.
Right in the beginning. Yeah.
Yes. So we have done both kind of material. Yes, here. So you can see there most of the are which we are using. So, and one more thing which I wanted to say here is that this YAG when you are using YAG, so yttrium aluminum, both are low Z materials. Here we want to have very high stopping power. So that's why high Z materials are more used. So because I said that density has to be large. So gadolinium, lutetium, these are high Z materials, and that's why they have got more application in medical imaging basically. But we are using yttrium aluminum perovskite in our normal radiation application because when we are talking about the stopping power, we can stop any given radiation, but we have to increase the interaction length. So I can put like a 50 mm long crystal to stop a 511 keV photon. But if I am putting that bigger crystal, but then for medical application, I cannot put because it has to be a compact system. You are putting a patient inside that, and then you have to house it inside, and then you have to have make a array. So that's why generally we are going into those material which has got very high density, and there yttrium is losing. So that's why in all this application we have used high Z materials.
Thank you.
One more question is, you talked about film based material detectors, thin film detectors. So how is it? Is there any specific advantage or disadvantage with respect to the crystalline detector?
Actually, thin film can be only used in radiography, where the energy is very less, because the film thickness is like 200 micron or maximum 1 millimeter. You cannot go beyond that. So whenever it is only used in radiography kind of, where your X-ray plate is there. So there we can use thin films. And the other is that because and this thin film is only used for cesium iodide. It is not used for any other scintillator material, because as I have told that cesium iodide has got this of growing into this needle-like structure. So I don't need to make these arrays. These pixels I did not make because it has got the natural arrays coming out because of this kind of needle-like structure. But when I'm going to any other high energy radiation detection, I cannot use these films. So that there is a trade-off, and because making films is easier, cheaper than growing a crystal and then cutting it and then making a pixel. So wherever it can be used, it is used, but it cannot be used everywhere. So it is like a trade-off.
Sarah madam.
Yes.
I have one basic question. Is this scintillating materials specific? Why? What is their specificity that they are scintillators? Is there electronic structure or band gap? What makes these materials scintillators, and why not others?
Yeah, actually, scintillator materials, you need a wide band gap, one thing, but you need a activator. Like cesium iodide per se, pure cesium iodide is not a very good scintillator. So I am adding thallium to it. So thallium is creating bands within its energy band gap, and this energy states are there within the band gap, and this energy state has got the property that it will be whenever electron hole pair is forming because of any high energy radiation, whenever there is a jump of electron from the valency band to conduction band, it comes to this energy state and it will decay fast. It will not trap, or the whatever this de-excitation is there, it will be a radiative de-excitation. It should not be a non-radiative de-excitation. Non-radiative de-excitation is like de-excitation through phonon mode. So then it will be just lost like heat. You will not get any luminous, any photon output. So two things is that when the de-excitation is there, it should give out a photon. So that is one thing a scintillator should have, and it should be fast. So whenever there is an incoming high energy photon is there, then it gets excited to the conduction band, and then from it gets lowered to the activator band and activator energy level, and it should come back to your ground state in a very small time. So this is a definition of a scintillator. So if you can find a transparent material matrix and use activators like that, so you can make a scintillator. So there is a lot of material engineering going on to make a very good scintillator, and for different application you use different scintillators, basically depending on their characteristic.
And one more question, ma'am. Yes. Is it crystallinity important for the scintillating materials? Why not glass, amorphous materials?
Okay, amorphous material, as I told you, what is happening in a scintillator, you have to collect the photon which is coming out. Now, for that you need a transparent material. So ceramics are not generally transparent, but okay, then there are transparent ceramics which is coming out. But basically transparency is one thing which is important for a scintillator, because you have to collect the coming out, the emitted photon. So that's why you need transparency. So that's why you can use a glass also. But then the second point comes, which is not very important in medical dosimetry, but when I am doing a radiation detector kind of thing, I have to also find out the energy of the incoming photon, like the gamma photon it has come, whether it has come from a uranium or it has come from a plutonium or it has come from a cesium. All these gammas have got different energies. So to find the information of this energy, you require a crystal field, which can be only found out in a single crystal. You cannot do it with a glass-based scintillator. So there are glass-based scintillators, but it can be only used as a counter, not as a spectrometer, gamma spectrometer and all those things. So depending on application, I would say.
Okay.
Good afternoon, madam. You work only on scintillators, or CZT? From the literature, it is found to be having better features compared to these. So you have not worked on CZT?
No, myself, I have not worked on CZT. I'm working only on scintillator crystal. CZT is a semiconductor detector. So maybe in the future we will take up, but not at present. I know it is very good material, but growth of CZT itself is very challenging. So we have not taken up. Let us finish off our work with scintillator and then go to a new field.
Okay.
Yes.
And looks like in India there is nobody who's synthesizing CZT.
CZT, some work is going out at IGCAR Kalpakam. So there is one crystal grower there, my very good colleague and collaborator, Dr. Ganesh Murthy. He is working on the growth of CZT.
Okay, thank you.
Thank you.
If there are any more questions?
Madam, one just last it's question
Sure.
on growth. In
Yes.
your beginning, you mentioned about thermal evaporation as one of the methods for growing single crystal, but on your graph, multi-single crystal feature that we see in that particular material, don't you think, I mean, is it advisable to have that, because then you will have a lot of artifacts, no?
No, the thermal evaporation graph which I was showing it is for the thin films of cesium iodide. But cesium iodide crystal itself, it is grown by the Bridgman technique, in which we have got proper single crystal. If you remember, I have shown one slide on.
Yes. No, now I got it. But I thought that was you were recommending for a single crystal, but you're saying that is just for a film. So that's okay.
So this is the film, so which is for normal radiography. This our plates, radiographic plates are there. But for our other PET application alone, this is the single crystals.
Yeah.
These are two different things.
Okay, thanks.
Welcome.
If there are no more questions, I take this opportunity to thank you, madam, for your insightful and thought-provoking talk. It indeed helped us all to deepen our knowledge and to think broader. You showed us beautifully the detailed process in which various materials are engineered as per requirement and systematically translated to be used in devices for healthcare applications of medical imaging and radiation detection. Thank you again for taking time out of your busy schedule. We look forward to hearing from you again, ma'am. Thank you so much.
Thanks a lot. Thanks a lot.
I once again thank all the speakers of the day. Thank you, Shashwati ma'am. We are happy. We are indeed. The morning session is going to be something related to what is happening in the Department of Physics of the Sri Sathya Sai Institute of Higher Learning. So I am just here to give you a quick overview of the biomedical and healthcare related research that has been going on in the Department of Physics. The history dates back to something around 2003 or 4 onwards, where department has actively taken up research in the area of biomedical side and also healthcare side. The first DST funded project technique that was used for identification of the microcalcification in mammograms, which generally otherwise is not visible. This microcalcification films and the radiography films. So that was the first project department that was headed by Dr. Shivshankar Sai sir. From there, using different physics principles in terms of applying the physics principles to research in healthcare, mainly diagnostics part. So after the DST project in that 2005-06 around that time, then we also had another project that was using the X-ray fluorescence and particle-induced X-ray emission techniques to look at the trace element profiles in the who are prone to diabetes in and around this Anantapur district of where the Sathya Sai Institute is situated. So the aim of that work was to profile the blood in terms of the trace elements and see what kind of deficiencies are there in the trace elements in the diabetic group and the control group. So that was a very good project that came out. Though we didn't pursue much, we used the facilities in the IG car for the particle induced X-ray emission, but after that we have not continued that work, but we are doing something related to that using the tabletop X-ray fluorescence support which we have in the department. Later on, the department also took up research in other in biomedical and healthcare related areas by applying various other physics principles like spectroscopy, Raman spectroscopy, and interference, optical interference. All these things over the last 15 years have resulted in very good funding for the department. It will attract close to around 9 crores in the last 10 years in terms of external funding from DST, DBT, SCRB, DAE, BRNS, etc. And of course, they have also resulted in these research activities have resulted in very good publications and also prototype devices. So, given this background, I just now request my colleagues to come and quickly present some of the current research activities that are going on related to biomedical. Invite Dr. Murli Ravi to present his work. Professor Dr. Shashwati Sen has just mentioned about it since we are collaborating with her, and this is a continuation of the work which was also previously done. So Dr. Murli Ravi will present, and after that I invite Dr. Denny to on OCT relate this application. And then we will have Dr. Abhishek who is actually pursuing his PhD. Shri Abhishek, who is a colleague from our Brindavan campus, not the last, but definitely a very important work which is going on is led by my colleague Dr. Muthukumar. So I now invite Dr. Murli Ravi. Sai Ram.
Sai Ram to everybody. With respects at Swami's feet. Thank you, sir, for introducing me. Although I had a different slide deck for presenting today, after listening to all the speakers, I thought that I'll relate to the speakers in terms of the work which we are doing. So there are different portions which the speaker spoke, and we are also working on some portions like that. And so I thought it will be more relating to the students and more. So as Gauri sir told, that we are working on SciGC, which is a portable high-resolution gamma camera for functional imaging. And Professor Shivshankar Sai is the head of the group. And there are a lot of people who have contributed to this field. And I like to thank all of them. We also place on record the funding received by many may be wondering, there are so many imaging modalities, why do we need one more imaging modality at all? So this is the image got from a CT machine. You can also relate it to an image got from an ultrasound, though the physiology won't be the same as 2 days. And this is from the SPECT machine, that is the nuclear medicine machine. You can also relate it to the PET machine, which is working on the similar principles but not the same. So what you get from here is, if the patient is alive or dead, you get the same image. That is anatomical information you'll get. And in the SPECT machine, what you get is, if you get the metabolic information, that is how much of the organ is actually working. So it is very important in terms of imaging deficiencies like cancer, where more metabolism happens around that region. So you can accurately pinpoint to the place where the cancer is there. And this is very important in those areas. So I'll just play a video of what is actual gamma camera, because I don't have much time to cover, so I thought I'll play an old video which we made some time back. So this is how gamma camera works. An audio. question was asked previously, which isotope is used. We typically use technetium, which is 140 keV. This is the molecule. The isotope travels wherever the blood travels. That is a very distinctive feature compared to the other imaging modalities which was described in the past 2 days. So what you get is functional information from the organs. So the isotope reaches the cancer region and continues to emit radiations from wherever it has been deposited. We typically tag it along with like how Shashwati ma'am mentioned, with glucose, so that the metabolism is more accurate. So the isotope reaches and it continues to emit from those regions. These radiations come out from the body and are picked up by the gamma cameras, and images are produced. And this is a typical large field of view gamma camera, and the detector goes around the patient producing tomographic images.
The size of the gamma camera for usage in operation theaters, new age materials were simulated, and properties such as photon yield, the point spread function, blood field uniformity, stopping power, etc. were studied. In view of all these factors, cadmium zinc telluride was chosen as the detector material. SciGC has about 2000 pixels of CZT, each of which measures just 2 × 2 mm square. SciGC can reduce the imaging time by about 20 times and also lowers the administered isotope dosage. This has led to increased patient comfort. The clinical validation, performed in collaboration with HCG Cancer Hospitals, proved that when compared to the typical state-of-the-art device, GE Infinia Gamma camera, which costs about 5 crores, SciGC, at a cost of just 40 lakhs, produced concurrent diagnosis with images of greater detail for all the enrolled 32 patients.
So the purpose of the video was to just give you glimpses of our previous work, so that we can I can present more of the present work what we are doing. So this is a large field of view gamma camera. It is situated in purpose-built rooms as big as this MMLC, and it weighs about 6 to 7 tons in weight, and it has it costs about 4.5 to 5 crores. The spatial resolution from these images, you can see this is a full body scan, and this is the full skeleton imaging. Okay, and you can see that the marked out regions of interest, you don't get high resolution images from these areas. So what the doctor typically does, this is from our own hospital, from the Siemens ECAM, and he just cuts out these areas and he reproduces the same images, which does not give us any extra information. And this is from GE Infinia model, which is from the clinical collaborator, and this is the thyroid images. Okay, so what we do in our group is we study the different factors which impede good production of a good image. That is spatial resolution, energy resolution, the detector type, the data acquisition system, and the image reconstruction algorithms. I wouldn't go much into it because in 20 minutes I won't be able to cover much ground. So just keeping some things which are of direct interest to the students, I just want to mention about the direct conversion and indirect conversion detectors. Shashwati madam mentioned about the scintillators. If you all remember, a scintillator is a indirect conversion detector. That is, the energy is converted to a photon, and the photon is converted to an electron, and with some electronics we'll convert the electron into some current, and after that the sampling happens. Okay, in the direct conversion detector that Professor Vijay Sai asked, it is CZT what we have used. It's a direct conversion. So the photon is directly converted to an electric current. So there are no multiple steps involved, and you save a lot of time in terms of dead time. That is the time which the detector is suspended for further acquisition. Okay, so you get more data rates basically. So what happens is, what we found is, in our study, what used to take 20 minutes for a specific SNR, we got the same data in about 1.5 minutes. So a person is coming for an imaging, for example, an old lady or a child, she cannot keep like this for full time, right? It is going to pain her. First of all, she's a patient, and for 20 minutes she cannot stay static like that. So if it's a 2-minute detector, it is much faster and increases patient comfort. And other things are, it gives more quantum efficiency. Someone mentioned that it is 12% and this is 35%. So you have more data collection which happens. So the SNR is again better. So we use the cadmium zinc telluride. I'll not go into the details, but it's a 10 mm almost by 10 mm, 10 centimeter by 10 centimeter field of view, which is very apt for small area imaging. Then another thing which should be of interest to the physics student is how we manage the data acquisition system. Thinking about a term called afterglow. Afterglow is something which comes with the scintillators. Typical scintillators have a long tail end, so they have a long decay time. So when you have many events which are happening, what we are interested is in the peak of the signal. So when all the tails overlap, you have a false signal which is produced. So we should not be having that. So what we do is we have something called pulse shapers. So pulse shapers is basically RC circuits, and it is typically made for that scintillator. So it's almost, you can think it of a convolution. So you convolve the signal with this and you get a signal which is of your interest, the time which is of your interest. So what happens is when you have a long pulse, your data acquisition speed comes down. So all these things are there in the current state of our devices, but the thing is, it's all in the analog domain. So once you change the detector, again you will have to change the whole electronics, and each pulse shaping circuits will be like as tall as this roof. So it goes on and goes on, and you have, that's why you have the big purpose built rooms for such kind of devices. And one more problem is when you want to make it a small miniature device, you cannot have such processing units to process your signal. And when you have analog system of electronics data acquisition, the whole system is suspended until the event is captured. So if you want to capture a second event, you'll have to wait until the whole event is digitized. So this is called the dead time of a system. Dead time is directly related to the acquisition speeds. So what we did is generally all these pulse processing circuits produce an event, and then the sampling happens. The ADC converts it to a digital image. So in our setup, what we did is we shifted the ADC from the tail end of the circuit to the front end of the circuit. So what happens is you have lots of data which comes. Lots of data. So typical 1 minute acquisition will give you GBs of data. So you have billions of events which are happening per second, and everything is sampled. So that's why that's why I mentioned about fast data acquisition speeds. Also fast data, you get a lot of data. That's what I'm trying to say. And what happens is you have many algorithms which can be written in the software. You don't need to depend on the hardware. So once implemented, it's not done forever. You can always change the algorithms and try out new things and manipulate. This is finally it's in the digital area, right? So these are the advantages. So this is what we have done in our SciGC. And coming to image reconstruction, this is the final thing, which is once the image is, the signal is sampled, the image is made. So everything comes in a serial way, right? So we'll have to convert it back to an image and decide where the scintillation happened and localize it to that area and create an image. So coming to CT, MRI, PET and SPECT, I'm just putting what are the complexities involved. I'm just trying to show you that. In CT, CT has a emitter outside. It has the organ, the body which is of interest, and the detector which is again outside. So CT produces X-rays, it goes through the organ, and then it comes to the detector. So your direction is in your control, in what angle you are emitting. So you will expect the event to be detected and the exact angle on the other side. You know what energy you are emitting. So 30 eV or 30 kV or 40 kV, depending on the study, you know what energy you are emitting, and you know how much intensity is also. So once it goes through the body, you know how much of intensity has been lost in the body. So you can always map it back to what is there inside the body, right? So this is CT. How MRI works is you have high magnetic fields around the body, and all the OH ions orient towards that magnetic field, and once you switch off the magnet, the dipole moments, you will capture the dipole moments, and from there the image is formed. So you don't know the direction, in what direction the dipole will be relaxing, but you know the energy, because a typical OH ion, you know how much of dipole, whatever you call the energy, it will be relating, and you know the intensity, that is what is you're expecting. In PET, you don't know the direction. You know the direction of which it is, because Professor Shashwati mentioned it is 511 keV, 511 keV positron electron annihilation, and it will come in 180 degrees apart. So you know the direction, and you know the energy. It is 511 keV only, but you don't know the intensity. But coming to our imaging, that is the SPECT imaging, you don't know all the three. Because the radioisotope is inside the body, it emits a spread spectrum. So you don't know what direction it is emitting. It will emit in all 4 pi directions. You don't know the energy, and you don't know how much of each energy is coming also. So that's where the image reconstruction is a very, very complex procedure when it comes to SPECT. So one way of doing it is using Fourier transform based filter back projection, that is the FBP algorithm. But see, FBP algorithm, you have this, it works very well if you, yeah, I'll go through this first, then I'll come to that. If this is your body, when you look at it from the direction where P is written, you will see this image. When you slice it, yesterday professor was talking about slicing, right? I think Professor Fanindra was talking about. So this is the way you see, when you see it in this angles, right? So, and later you traverse the detector and the source around the body, and you connect multiple snapshots of the same organ, and you reconstruct your image. But the problem is, in gamma cameras, the source is inside the body. So it is not a transmission kind of imaging, but it's an emission kind of imaging. So FBP doesn't work well with transmission kind of, with emission kind of imaging. So FBP produces a lot of artifacts. The advantages, you have a lot of good speed, and complexity is less, and so these are the advantages of FBP, but it doesn't translate to much amount of purpose, because it produces blurred image due to the artifacts and all these things. So we use something called maximum likelihood estimation maximization. You create an estimator matrix, and you are telling this is what I'm expecting, and you keep seeing the detector data, and you keep updating the matrix. That is basically a model of what you are expecting, and this process iterates through the scan, and you produce images. But the problem is, it takes a lot of computational power. Okay, it produces great images, but it takes a lot of computational power. Yesterday, Professor Panindra was telling about image reconstruction and computational methods which are required for this. So we are working in that area also, and we use something called field programmable gate arrays. So just to typically give you the amount of time it takes to run on the i7 processor, it takes about 3.3 hours, and to work on the workstation, it takes about a few minutes. So think of this setup. Okay, you have told the patient to take an image, and you're waiting for 3.3 hours for an image to come out. So this is not going to work out, right? So that's why this algorithm is not used. But what we did is, we used an FPGA, and some sequential computing tasks, we pushed it to the CPU, and we took the most compute intensive task and we pushed it to the FPGA, and this is called hardware acceleration. So you use a specific hardware, and you say, please compute this and get back to me. So this is the hardware accelerator, and it takes specific tasks, only specific tasks, finishes it and comes back to you. So we could push a lot of blocks, you can see these 5 blocks, into the FPGA part, and we could achieve an acceleration of about 288 times. So the 3 seconds it takes almost to compute an image from few hours. So this is what we could do, and we could publish it in very reputed journals. And the next part is the images form, but you have to make the segmentations and create a sensible reading out of it. So this is called image processing, right? And what we found out is again taking a lot of time, because the data is huge. So we used a very different approach. That is, we used the analog devices chip called BF609, and this chip is used for ADAS, that is automatic driver assistance system. And basically what it does is, it says vehicle is in front of you, there's a woman crossing the road without taking any precautions, and there is a vehicle approaching in the other end, and there is a speed limit, but you're going beyond your speed limit. So these are the things which they typically used. We used it for our applications. We sent the images to the BF609 to compute the parameters what we are asking and come back to us with the results. So we could get about 250% acceleration, and it was an invited paper in IEEE. So we implemented all these things in our SciGC, and this is the prototype, and you can see it's about 6 feet tall. Okay, so this itself was an achievement, but coming to the later aspects, from 6-ton machine we could get it down to 300 kgs. This is SciGC for you. And later, yeah, someone was speaking yesterday about the phantom trials and all that. So this phantom, this called the picker thyroid phantom. It's about $7,000, which is about 4.5 to 5 lakhs. So we designed our own phantom with our own knowledge, and we could get it down to around 15,000 rupees. So these are the images from the phantoms. It basically simulates, or not simulates, it emulates a thyroid organ, but actually not using a human, but using your own some setup. Okay, so these are the phantoms, and you can see the tomographic images from the phantom. And coming to one interesting observation, if you can see, this is imaging from SciGC of the same phantom, and this is the imaging from the GE Infinia camera. Okay, you can see that 2 mm is clearly demarcated, and it's imaged in the SciGC, but in GE Infinia you don't see that at all. So how does it matter? You may ask, so what is the great thing in 2 mm? Other things are there, but the important point is, yesterday someone was mentioning about in mammary cancer, it's the most easiest cancer to deal with if you detect it at the right time. So how do you detect it at right time? You detect it when in early stage. Okay, so when the cancer is still growing. Okay, so basically the patient will come, they'll take the scan with the GE Infinia, they'll say, yo, you're fine, just take these tablets, and they'll send away. But after 1 year, they'll come with a bigger problem to deal with. If we could deal this problem 1 year earlier, we could have saved that patient's life. So that's where it is important to image smaller areas of interest at an early stage. So we did our clinical trials with HCG Cancer Hospital, which is the leading cancer hospital in Bangalore. And Dr. Vishal Rao is our collaborator, and he is the face of COVID research in South India right now. So he was our collaborator, and I think you saw these images in the video, but I'll just explain to you in one or two slides. This is the image which we got from the one which you see in the color, which is got from SciGC, and the one on the right side is a black and white, is got from the GE Infinia model. So you can see in the GE camera that all the intensities are not clearly demarcated. So you can see a block which is called thyroid. How much of the thyroid is actually, which portion of thyroid is functioning more, which functioning is less, it is not clearly seen. Though this was not a very important, it was a Graves' disease and a slightly hyper-functioning thyroid gland, so it was okay. Now you can see this is from SciGC and again from Infinia. So, but what if you feel that, how do you demarcate between a hyperthyroidism and a thyroid cancer? That's where SciGC comes into picture. Okay. And this is one more data which I thought you should be interested in. SciGC, so the GE gamma camera told that there is no thyroid organ at all. So this person didn't have a thyroid. It is called thyroiditis, but SciGC picked up the signals from the thyroid, which is still available, which was still there, and it produces some of these images. So this shows the sensitivity of the device. So what next? So many people ask, it's all done, what you're going to do? I don't. So, but think about it. See, this is a 3 or 5 ton machine, and this is a 300 kg machine. But this one will still not fit into this scenario. This is the operation theater, and you will not fit into the scenario where you're going to take so much of real estate, right? So we are working on making a machine which is very, very small. That's a handheld device. So it will be as much as your deodorant bottle. Okay, so this is what we are working on right now. And How is this helpful? Okay, so you may say ultrasound is there, everything is there. How is it going to be helpful? Okay, so let me tell you one thing. You have, I'll tell you how it happens. The patient goes to an imaging center, and clearly it is marked where the person has to get into an operation. But how much of it is in the operation theater tomorrow? How much of the organ is actually removed? Someone was telling yesterday about the finesse of hands of the doctor, which is very useful, right? So when you open up the body, it's all shades of pink. So what is a cancer? What is not a cancer? What was exactly removed? Are you removing more as a matter of precaution, or you are removing less and leaving out the traces of cancer back into the body? And the patient will come back with the recurring symptoms, and you'll say, "Oh, sorry, I forgot to remove everything. I'm going to make one more surgery on you." So there is no validation of an operation. So we are making this handheld device. So after the operation, the doctor will have it next to him, and he will keep it again, and he will check if all the areas of interest which are supposed to be removed are removed or not. So we have a two-pronged approach for this. One, we are using a gamma, and one we are using NAR imaging, fluorescence imaging. So I'll come back to it. But how is fluorescence? No, one more thing is, if there is one more node, secondary node, which is at some depth, how will you be able to image it? So these questions will be answered in our new prototype. That is, this is a gamma detector, and this is a fluorescence detector, and both the signals gamma and NAR will come together, and we have some routing which takes place, and so what you get out is a composite image of gamma and fluorescence. How gamma helps is to give you the depth of the traces of cancer which are there in the depths, and fluorescence gives you the pictorial information. It gives you immediate information of what is there on the surface. So one more area which we are working on is on replacement of mammogram for breast cancer imaging. So you can see in this device, in this image, that is on the left of the second image, you can see this from an X-ray mammogram. A mammogram works basically on X-rays, but if for ladies who are above 50 years of age, there are typical symptoms which will make their mammary glands more dense, more fibrous. So the X-ray gets scattered here, and it will not come out. But the cancer is still there. It is not being shown out. So we are using gamma imaging for that. You can see here also. So it's like a wolf in the garb of a sheep. So you will not be able to catch it at all. So unless it expresses itself very openly after some time, maybe after 1 year, 1.5 years, you will not be able to. So this is one idea which we are doing. Thank you very much. If any questions are there, I would like to take. Yeah. So next one is Denny, sir.
Hi, Ram. I will make a brief presentation about the work on optical coherence tomography. I am pursuing my doctoral research program under Dr. Sailesh Srivastava in the domain of spectral domain optical coherence tomography. First, let us see what the physics of spectral domain OCT for a brief. So the SD-OCT setup is based on a Michelson interferometer, which and in one of the instead of the mirror we have a sample, and we have at the output we have a spectrometer. So what we see is that the output intensity is the what we get from two beam interference, and we see it this as interference of equal wavelengths. So if you have a specific reflector, if you have a delta reflector at a specific depth, that will give us to a fringes like fringes, which if we do a Fourier transform of that, we can get the position of the reflector which is shown here. So that the two graphs which is shown on the left is a reflector at one depth, and on the right is the reflector at another depth. So we can get the information regarding that from Fourier transform. So this is the basic physics of a spectral domain OCT device. If you compare this with other imaging techniques to ultrasound and confocal microscopy, we see that the confocal microscopy has better image resolution than OCT, whereas ultrasound has better image penetration. So OCT sits somewhere in between both of them. Now, so what do we get? So these are terminologies borrowed from ultrasound, which is used in OCT. So the depth profile along line depth profile, what you get is called an A scan. And if you stitch together various A scans of the sample, we get what is called a B scan, which is a cross-sectional depth image. And then if you have stitched many of the B scans together, can give you a 3D image or a tomogram. Now coming to biomedical applications of OCT, the main application is in the field of ophthalmology, where the OCT device has become a standard diagnostic equipment. It's also used in cardiovascular field. Apart from that, some of the fields which are upcoming fields are in skin and skin dermatology, dentistry, pathology, and gastroenterology. Here we are looking at not the high-end research for OCT where very high resolution and very high cost, but we are going to look at a specific niche application where we need not have very high resolution, but what is required for us, we are looking at ear imaging. As you might have seen that Dr. Anshuman had talked about middle ear. So we are also looking at imaging the ear. Now, one of the successes why ophthalmology, the OCT is used successful in ophthalmology is that the eye lens is transparent to light. So here also we see that there is optical access because the after the ear canal, that first what you see here, the eardrum or the tympanic membrane is translucent, and then we have the three bones, malleus, incus, and stapes, right? So in the previous talk by Anshuman, we had seen that how this is helping us to hear the working of this. So now, what is the problem here which we can solve? So the concern here, conditions of concern here is, even otitis media, Anshuman had talked briefly about it. It's a biofilm or bacteria film which is getting on the tympanic membrane, and that can cause diseases. So we would like to know the membrane thickness or the curvature of the membrane, which in the case of chronic otitis media. And another case is the case of osteosclerosis, where the stapes or the innermost medial bone is stuck and cannot vibrate. So it's possible that all other things are working and only this the stapes is stuck. In such a case, we could, if we are able to know whether if this is the only case, then that can be known by using a vibrometry technique. So these are the two problems which we are trying to tackle using OCT. So this shows the schematic of the parallel FD OCT setup that is used. So we see that we are using a superluminescent diode, 850 nanometers, and we have the Michelson interferometer. You can see that instead of one mirror, we have the speculum for placing the ear. So that is the sample, And we also see that the spectrometer is constructed from a grating and the camera, and we have another camera for survey to be used as a viewport to know which place we are looking at. So here are some specifications of the low-cost SDOCT that we have developed here in the department. So which has a axial resolution of about 20 microns, lateral resolution for 40 microns. In tissue, it has a penetration depth of 1 millimeter. Because of scattering, we cannot go more. Whereas if it's a transparent media, we could have a depth range of 6 millimeters. This depends on the resolution of the spectrometer that we are using, and the cost of all this is around $2,000. Whereas typical commercial OCTs which are used in ophthalmology, it comes around $50,000 or $100,000. So there is a large, we are able to cut down the cost by a large. Okay, so that's regarding the OCT, and I talked about vibrometry. So how we could the technique that we learned that was used to detect the vibration of amplitude is called the J0 technique. And you see the second term, which is the interference term. If there is a vibration of a particular amplitude m, and we see that from the mathematics we can see that it is the second term could be expanded in terms of Bessel functions, and we see that if you look at the Bessel functions, the J0 of x, which it has a 0 at 2.405, and if you choose the amplitude of vibration such that it's equal to that value, then we could see that the second term can be made to vanish, and this could be used to sense vibrations. So more details of this is available in the paper which is published. So I would also like to tell that this work of OCT in our department is pioneered by Dr. Harinanda Kumar and Dr. Sailesh Srivastava. And I would also look, this shows the viewport camera, the line which you see here, and this shows the corresponding B-scan image of a human ear, the tympanic membrane. You can see that the thickness of the tympanic membrane as well as the curvature can be seen from the B-scan image. And I'll also try to share some of the other publications by from the department. Regarding same OCT, and I would also like to acknowledge the postgraduate students who worked on this during the last few years. K.S. Aditya, G.R.R. Rohit, Swaroop P, Satyaprasanna Malik, J. Sai Prashant, and Kaushik P. Students were also contributed to this work. Thank you, Sarah.
To everyone. Since we are short of time, we will have the remaining two presentations post lunch. But when we come back after 1 hour, we will have the talk as scheduled by Professor Hakan Engquist, and then we will also have the talk by Dr. Chaitanya. And after that, we have an interesting panel discussion which is coming up. So depending upon how the schedule goes, the remaining two presentations by Dr. Abhishek and Dr. Muthu will be either just before the panel discussion or after the panel discussion. So we will now break for the lunch. I request all of you to kindly join us back by 2 p.m. The next talk by Professor Hakan Engquist is the professor is from Sweden. Is a very accomplished person. So I request all of you to join in time by the time the speaker is ready online. Okay. So we will now break for lunch. Thank you. Sai Ram.